1 year ago.
All right, good morning, everyone. Sorry for the little bit of a late start. I hope that you guys have had a good week of hacking. I apologize for some of the issues that we had with the numerical licenses, but rest assured, just submit what you can this week. Most of the students are in the same boat, so you're not really at too much of a disadvantage. I want to say also, you guys should be really, really proud of yourselves for what you accomplished over the course of this week, because you guys learned completely new software, attempted, solved hardware challenges, which are like big questions that are still open today. And it's not easy to do that in the course of a week. So what I'm going to do now is, before we get started, I'm just going to walk you guys through what this weekend is going to look like in person. And I'm going to give you some idea of what we have here at McMaster, because I know that not all of you are McMaster students here today. So we'll get started. So right now we have our opening remarks, which is just going to tell you how the weekend is going to run, tell you all about our facilities. At 10:30, we have a speaker from HardHaQ who's coming in to give a keynote and tell you all about the hardware that they have over there. From 12 o'clock to 3 o'clock, we kind of have a free block where you can continue to work on your challenges and networks with some of your peers in person. Concurrently, while that's going on, we're also setting up posters in the main room. So there's going to be a research poster showcase where you guys can go. You can see, talk to the people that are hosting the posters, and you get to vote. And the winner of the poster showcase gets $200. Second place gets $100. So check it out, see what you think is cool, ask lots of questions. Concurrently, at the same time, we also have CEDT tours. So CEDT is our Center for Emerging Devices and Technology. I talked about this a little bit last weekend, but it's the place where we have all of our cool engineering, physics, science going on. So we fabricate all of our solar cells. We have like MBE machines. We can grow quantum dots. I'm not sure. I think part of the tour you might also get to see our accelerator building. We have a particle accelerator on campus. This is definitely not part of the tour, but I will advertise it for you guys. If you like come back later to McMaster, we also have a nuclear reactor on campus. And McMaster is actually one of the very, very few facilities in the world which has an open pool nuclear reactor. So at some point, you should definitely check it out. You can actually see the Cherenkov radiation like coming out of the reactor with your own eyes, which is really, really cool. So that tour, for safety reasons, can only take 30 people. So it's going to be first come, first serve. So sign up as soon as you can. The QR code is going to be posted like right at the end of this slide deck. So yeah, make sure you get on that if you're here in person. And the way that's going to run is it's going to be 10 people over the course of 3 hours. So 10 people from 12 to 1, 10 people from 1 to 2, and then 10 people from 2 to 3. At that same time, there's also going to be, like I said, a work period. We have this room booked. We have the lecture hall just adjacent also booked. That's where all the food is. We have 3 workrooms that are booked on the opposite side of the Tim Hortons. So those 3 rooms against the back wall, you're also free to go in and work in. That might be better for some of you because this room doesn't have outlets. It only has the 2 at the front and then the 2 at the back. After that, we're going to come back to this room and we're going to have our industry talks. So unfortunately, the rep from Kothar had to cancel this morning, but KeyNet, IonQ, CMC, and QAP are coming out. and they're going to talk about all the cool stuff that they do in the field of quantum, what they're all about. They're going to give a half an hour talk each about what each one of their companies do. After that, we're going to lead a panel where we're going to ask them questions. You're going to get to ask them questions. And then there's going to be an industry night where you get to go talk to them, network. And yeah, I do want to mention also that the rep from Kothar, even though he said he couldn't make it, he's still open to requesting CVs from students that are interested. So if you are interested in that, you can contact us at quantum@mcmaster.ca, and we can put you in touch with James Lambert, who's the representative from there. And yeah, there's dinner going on at the same time. Don't know if I brought it up. There's also lunch. Those are both going to take place in the room just adjacent. And yeah, as I mentioned, one of our big facilities we have here is CEDT. The picture in orange, I believe, is our clean room. So this facilitates the optical, electrical, mechanical, biological properties of semiconductors and all related materials. You can't see it in this picture because this is a daytime shot, but when the lights are turned off at the very bottom of this pool over here, it glows bright blue. And also McMaster in the basement of ABB, which is a building that's across campus, has CCEM, which is the Canadian Center for Electron Microscopy. Sorry, Canadian Center for Electron Microscopy, which is one of the state-of-the-art electron microscopy facilities inside of Canada. So here's the QR code. If you guys want to sign up for the CEDT tours, I'll leave this up for like 2-3 minutes to let all of you sign up. And yeah, at the posted time for you to sign up, we're going to have runners that are going to go from the front of MDCL, so where you signed into JHE, because the tour is going to start in JHE. JHE is our engineering building here at McMaster.
Hello,
Okay,
Keith.
cool.
Sorry to interrupt
I
you.
would like to give one last thank you to our sponsors for making this possible. So our title sponsor is IonQ. We also had our academic sponsor, University of Sherbrooke, who very graciously provided us with the ANSYS HFSS problem. Xanadu helped us with our numerical problem, and they are also sponsoring the winners of the numerical challenge. So you'll get some special Xanadu swag for that. ANSYS, CMC, ComSol all made the licenses possible for this week. So this wouldn't happen at all without them. And our food vendors and McMaster Engineering as well. So McMaster Engineering Society, the faculty, Shawarma Royale, and also banh mi. So, sorry, that is a later slide. With that being said, we will pass it off to our speaker from IonQ. Hi. Here.
Can I come to my laptop?
Do you happen to have your slides on a USB? Because we're streaming it online as well.
I see. So it's on Google Slides. Can I send you the link and then can you
Sure.
open it?
Yeah, yeah. Sorry, just give us a moment while we get set up.
Or I can join the call too.
Oh, yeah, yeah, that could work as well. That might be easier. I can just send you the link. Sure.
Or can you just join the call and
Yeah, there's an HDMI today. Actually, I think the link should be sent to your
on the
email. Yeah, yeah. Yeah. Oh, yeah. I can, you can connect, yeah, to everyone. I can sign it. Unless you have them.
I should.
I don't think mine.
Emily, are you still in the meeting call? Yes, I'm. Okay, I got booted. I'm not sure how, because I started the meeting, but I just wanted to make sure it's still running. Is it still recording as well? Yes. Okay, great. Yeah, that's all. Um, yeah, no worries.
Yeah, 5 minutes.
Yeah, it's just. You could connect to my phone hotspot.
Or maybe I do have it.
Oh, okay.
No, I'm just worried if it disconnects.
My
The
Wi-Fi.
phone signal is.
Oh, okay. My Wi-Fi is also actively used right now. It keeps connecting to this.
Are you also like connected to the room?
I'm connecting to the McMaster Wi-Fi, so. But,
You wanna try connecting to McMaster?
yeah. Okay. Um, yeah, and I'll show you if it has internet connection. So I.
Yeah,
Maybe you can. Yeah, yeah, sure.
Yeah.
Oh, actually, sorry. You said it was Google Sites. Can you share it with the different account? I'll share it with my Google account.
Oh, okay. Got it. Oh, no.
Okay. That's good. Okay, so let's try this and speak into this microphone.
Oh, you don't have a color?
No, no, sorry. We
That's
have-
okay.
Yeah.
Can I put your laptop maybe here?
Sure. Yeah. If there's room, yeah. We can,
Seems better.
oh, it looks like the HDMI disconnected.
I did.
Unplug it in, just plug it in.
Perfect.
Okay. Cool. And
It says screen sharing stopped because external display disconnected.
oh. Okay. Okay, Emily, can you see the screen? All right. Okay.
All good? Perfect. And close this.
Here, if you want to use this mouse. Okay.
Sure. It's fine.
Okay.
Good. Yeah, thank you very much. Can you all hear me? All right, perfect. Yeah, my name is Sainath. I'm a senior scientist at a quantum computing company called HardHaQ. We use trapped ions as a primary platform to develop quantum technologies. So today I'm going to talk about how you can use a bunch of individual ionized atoms in vacuum as a platform for quantum computing. So I don't want to be this yet another boring lecture. So at the end of this talk, everyone, no matter where you start from, you should be able to understand how ions can be used as qubits, what kind of like cool stuff you can do with quantum, and in the end, you should all walk away with a feeling that quantum is cool, accessible, and hackable. So before I dive in, I want to like understand the audience here. So how many are like how many think that you're beginners, as in like you have heard quantum but you don't know what it is? Okay, a few, cool. And then how many are like intermediate that you understand like some quantum physics? Great, great. Yeah, and then any experts who know more Mormons and gates and stuff? Okay, perfect. Yeah, no worries. Yeah, I think I just wanted to gauge the audience so that I'll keep my talk fluid. And so feel free to interrupt. I think we have plenty of time. Feel free to interrupt me at any point to if you don't understand something. We can like take the talk like wherever we want, right? Okay, so let's dive in. Before I start my talk, I want to quickly introduce about our company, HardHaQ. So we have a single mission to develop world's best quantum technologies to solve some of the most complex and impactful problems. That's our like main goal. Um, Even though many people think that HardHaQ is just a quantum computing company, um, we work on like a complete platform. So over past few years, we have acquired various different companies to invest in not just quantum computing, but quantum networking, sensing, and also quantum security. So we even have like 2 satellite companies in IonQ that successfully launched satellites. So we do lots of stuff. So we even develop precise optical clocks that are space qualified. We even develop chips that are like random number generators that are in Samsung phones now. So yeah, we do lots of things, though our main business is quantum computing. And I will be focusing mostly on that today. And maybe briefly, I'll talk about quantum networking in the end. Yeah, so because of this like whole investment, we are like focusing on this whole networking ecosystem, which contains, let's say, the compute nodes and various devices to make these computers connect to each other. So the computers can be connected. Yeah, go ahead. Yeah, yeah. Yes.
Yeah.
I'll I cannot move it. Oops.
Sorry, my clicker is kind of messed up.
Yeah, okay.
Okay.
But it's okay. It blocks for the audience. Cool. Yeah, where was I? Yeah, because of this investment and exploration, like all these fields, we are focusing on like a full ecosystem where you have the quantum computers as the nodes, and you also, can you see my pointer? Yeah, okay, cool. So you can have the quantum computing as quantum computers as the nodes, and then they can be connected at short distance for distributed quantum computing, but also at large distances, like many kilometers or across the globe, to do cool stuff like blind quantum computing, where uh, like people, users with a quantum computer can submit jobs into another quantum computer where the other quantum computer doesn't know anything about your quantum algorithm. So they're like cool stuff. And also other things like QKD or time synchronization, and then so on. Like, so of course, I'll not be talking about every aspect of the quantum network. I'll be mostly focusing on quantum computers today. So even we started about 10 years ago, and we have rapidly expanded now with all these different platforms that we are working on. We are truly global today, mostly focused on US and Canada, but also across Europe and Asia as well. So if you want to work in IonQ, you can be at any of these places and do cool stuff. Yeah. Okay, so that was sort of quick intro about IonQ and what we do. So I'll jump into like, because there are some like beginners in the audience, I'll quickly talk about, okay, some quantum computing basics so that you don't miss out on the whole talk, right? So if you have never heard of quantum mechanics or like don't know the main principles, there are a bunch of golden rules that you should understand. Number one, can you not hear me?
No, it's all good.
Okay. Yeah. Number one, quantum objects are like waves and they can be in superposition. So what does it mean? Like normal objects are sort of binary, or they can only be in one state, but in quantum mechanics, the objects can be in like a superposition of multiple states. So what does it mean? That they have, like, let's say there are 2 states, 0 and 1. They can be in combination of 0 and 1 with an amplitude A and B. And those amplitudes evolve based on the inherent Hamiltonian of the system. So if you don't know what Hamiltonian is, ignore that. It just evolves based on some environmental parameters. That's rule number one. So it can be in superposition of multiple states. So what does it mean? So rule number two is that, okay, it can stay in that superposition as long as you don't look at it. Immediately once you look at them, they collapse into one of their base states with a probability that is proportional to its amplitude. So if you have a state that is, let's say, 0 plus 1 with their amplitudes A and B, it collapses into 0 or 1 if as soon as you look at them. So it's the spooky thing. Immediately once you look at these quantum objects, they collapse into one of these. So that's the measurement rule. And the third another weird rule is the entanglement. So the main power for quantum computers come in comparison to a classical system is through entanglement. So what does it mean? When you have two particles that are entangled, you cannot treat them as a separate system. They are like combined together. They are highly correlated. So let's say you have an example. You have, let's say, two particles, A and B, and let's say they are entangled. This is one of the example entangled state. It's called a maximally entangled state. So if they are entangled, they can be in a state like this. So it's like 0, 0. So red here is, let's say, particle A, and then blue here is particle B. When they're entangled, what happens is, remember, there is a measurement rule, right? So as soon as you measure them, it collapses into one of the basis states. So if you measure A, and let's say it collapsed into 0, and always B will be collapsing into 0. And even though it's like kilometers apart, doesn't matter. As long as they are entangled, if A collapses to 0, B collapses to 0. And if A collapses to 1, then B also collapses to 1. So that's sort of, Einstein calls it as like spooky action at a distance. So for two particles, there are like four configurations, right, to the two. But if you talk about, let's say, 300 qubits, the number of configurations are more than the number of particles in the universe. So this is what gives the quantum systems the complexity. So in 1900s, the people wanted to like simulate this quantum physics. That's when people were like discovering quantum physics. They wanted to simulate or understand using classical computers, and people like Feynman said that, okay, nature is quantum, so you should use computers that are made with quantum principles rather than using classical computers to simulate quantum physics. You should use quantum computers to you should build computers out of quantum physics to simulate quantum physics. That's what is the main goal of quantum computing in the end. So basically, what is quantum computing is like you are using nature's language of qubits to do the computing. So because they can stay in these superposition of these like many states, you get like massive parallel computing for hard problems such as optimization. So that doesn't mean that you can parallelize any algorithm. So there are only certain algorithms that quantum computers are good at. It doesn't mean that you can parallelize everything, but for the ones that they are good at, you get like you get like high speed up compared to classical algorithms, because your algorithms are like going through all these paths, and then you have quantum interference that gives the advantage for computing. So again, this talk is not about quantum algorithms. We can have a different whole discussion how quantum computing can solve like problems like, let's say, optimization or like prime factorization, but we'll focus more on hardware, right? So not every, even though like you can see quantum phenomenon in like daily things, like in the fact that laptop is working, or like phones or even projectors are working, everything is decided by quantum mechanics. That doesn't mean that I can use a projector to, I don't know, make a quantum computer out of it. So there are like some important criteria which decides whether a quantum system can be used as a quantum computer or not. So this is a famous criteria by DiVincenzo, which talks about like 5 important things that a system needs to have to be qualified. It doesn't need just to be qualified to be a quantum computer. So hopefully I will motivate you enough, or like cover all these topics during my talk, how you can use trapped ions to do all these things. Like you should be able to initialize them. So you should be able to control these qubits and initialize them into whatever state you want, right? Like you cannot just like have the quantum particles and, let's say, not be able to control it. You cannot call it a quantum computer. So you should be able to initialize. And then second is they should have long coherence times. So coherence time is roughly, you can think of it as like a sort of how long their memory time, as in how long it takes for them to forget the information. So they should not forget the information, or else you cannot do much with them. So coherence time is sort of one of the important things that quantum computers don't have. So a quantum system should have long coherence times to be able to do any qualified like quantum computing. And then the fourth is they should have like universal set of gates. So just like classical computing where you have a bunch of logic gates, quantum computing is also made of various logic gates, and there is a universal set. What it means by universal set is that if you have those gates, you can perform any quantum computing algorithm as long as you can do those small set of gates really well. So it could be different for every platform, but they should have a universal set of gates so that you can do whatever you want. And then in the end, you should be able to measure them reliably. As in, when you measure these qubits, you should be able to reliably get the information out of the qubits. If the measurement result is lost on its way, then it's of no use. And I skipped the first one. You should be able to do all these things, and you should be able to scale it to large number of qubits, even like hundreds or thousands of qubits, while being able to do all this. So yeah, so these are like roughly the 5 important criteria a quantum system needs to have to be able to be a quantum computer. So from early 2000s, like there has been a race to build a quantum computer, basically taking a quantum system and trying to show that you can meet all these 5 criteria. This is an old picture which has only, let's say, 5 different platforms, but these days there are like a dozen different platforms ranging from superconducting qubits, trapped ions, neutral atoms, silicon vacancy, diamond vacancy, so on. In the end, the principles are very similar. As long as you can control these qubits and scale them, they can be a good platform. But we bet on trapped ions because of various properties that I'll cover about. All these platforms have their own strengths and weaknesses, but we think trapped ions are the best platform to that we can make a quantum computer out of. So yeah, we'll jump into trapped ion qubits. So before that, any questions on general, I don't know, basics on quantum computing? Any questions? Okay, go ahead. Right. So, for example,
Can you repeat the question?
Okay. So the question is regarding the 5th criteria of Da Vinci, just regarding the measurement. So the question is that how much loss you have in quantum computers compared to classical computers? Is that the point? Yeah, of course. Again, I want to quote someone, I forgot who said this. A quantum computer is so different from a classical computer. Okay, a classical computer is more similar to an abacus than a quantum computer similar to a classical computer. So the measurement is very different from different implementation, but the problem is you need to deal with single quantum particles. So it's like, for example, for trapped ions, they are photons. So you need to not lose, let's say, single photons on the way. There are tricks you can do, but whereas like in classical computer, if let's say you lost something, you can remeasure again. But in quantum computers, once you measure, then you sort of you lost the information. You cannot like go and measure again. So you cannot like lose the information on the way. That's not entirely true. It depends on platform to platform, and there are tricks you can do, but basically that's about it. And then also, because you're dealing with very, very weak signals compared to classical computers, there could be huge noise in the background. So you could easily mistake the measurement result compared to classical computers. But I mean, it was hard at a time, but now, for example, platform like quantum trapped ions or at IonQ, we could get like more than 99.99 fidelity on measurement. So we are good. But it's a problem. If you take a fresh system, you need to do lots of tricks to sort of mitigate that problem of measurement. Go ahead.
What's an example of the type of algorithms that quantum computers have advantage over in comparison to classical computers? And are there any sort of potential problems that we can solve that you are particularly interested by or excited by?
Right. So the question is, what can you give me an example of a quantum algorithm that can be calculated on a quantum computer better than a classical computer? And then what are we interested in as HardHaQ company, right? Right. So for the first question, there are various popular ones, starting from like Shor's algorithm to do like factorization, right? So classical computers, they take like exponentially long time to factor large prime numbers, whereas quantum computers can do it in linear amount of time and linear amount of resources. So that's one thing that you can do much faster. Then there are various like search-based optimization algorithms. And most importantly, what I am excited, for example, right, not just the company, is quantum chemistry. So for example, chemistry today, right, like if you want to, let's say, invent a new kind of paint, the way you do it is you go into the lab, you try a bunch of things, you mix them, you try to see you get something or not. Chemistry is very, let's say, it's a science that is based on trial and error. Like you don't know exactly, because you cannot simulate that in a computer because it's too complex. With quantum computers, potentially you can simulate the whole mechanism that you can, let's say, if I want to have a new kind of paint that has so and so properties, you can put that problem in a quantum computer potentially and get an answer much faster compared to trial and error. So that changes quantum chemistry completely compared to, let's say, what you can do now. And then there are like various interesting things you can do in like finance, optimization, and so on. Like there are plenty of them, but if you ask me what is the single problem that can be solved today, today's quantum computers, there is nothing. So we are trying to get there. So as in there are very niche problems that quantum computers have solved, but the quantum advantage, as in like, is there any practical use today that quantum computers can solve? There is unfortunately nothing. I should not say that, but unfortunately, but we are getting there. So mostly it's because you can use today's supercomputers to beat quantum computers, or the problems are really specific that it's like, okay, you don't have general use. But once you scale them up and once you reduce lots of errors, let's say once you get to the regime of like thousands of qubits, we hope to solve very many interesting problems. Go ahead.
What exactly is the crux of the problem that's stopping us from getting there?
I think I'll cover that. So the question is, what is the crux of the main crux of the problem that is stopping us in getting there? I think I'll motivate that during my talk. Yeah. I mean, someone said this, that, okay, there is like conservation of misery. So every platform has their own pain points that there is, I mean, even though I'm from HardHaQ and then we are betting on trapped ions, there is no clear winner yet that has emerged that can solve all their problems. So the problems are very engineering specific. So there is no fundamental physics that is blocking. It is a lot of engineering. And remember that quantum computing is one of the most challenging problems we as a humanity will ever solve. And I feel that in my lifetime that is possible. And it will be one of the biggest boosts in technology that we have ever made. No, I see nods. That's fine. Okay, cool. Yeah, let's jump to the next part of my talk. Unless you have more questions, we can discuss that later in the end of my talk, right? So, okay, trapped ion qubits. I'll be talking some basics about trapped ions and why we think trapped ions are great candidates for quantum computers, right? So, if you are not familiar with trapped ions, the picture on the right shows a linear chain of 64 ions. So, where each blue dot here is an individual atom, that is trapped in one of our chip traps. So the bottom gold color thing is our ion trap that is made of various like electrodes that apply various like oscillating and static potentials. So that applies some potentials to create a linear chain of these ions. So they form like a nice chain. And the advantage of these trapped ions compared to other platforms is that they're identical and naturally quantum, as in compared to other platforms, let's say superconducting or silicon vacancy or diamond vacancy or any other platforms, atoms have this advantage that they're naturally quantum. You don't need to fabricate them. They're abundant in nature. You just need to catch and isolate them and you have a quantum object ready. And they're perfectly quantum, as in superconducting qubits or whatever are, let's say, they're approximately quantum in some sense. So these are like perfectly quantum and they're identical. So why is that important? If you have like multiple qubits and they're not identical, you cannot entangle them really well. So they have to be perfectly identical. And if you fabricate them, you can have like fabrication tolerances that sort of adds up and becomes a huge pain in other platforms. That's one of the pain. And trapped ions or any atom-based quantum computers don't have that problem. So that's one advantage. And second is long coherence times. So I motivated that qubits need to have like long coherence time, right? So trapped ions have like, I think the best coherence time that was measured was hours compared to microseconds in other platforms, let's say superconducting qubits. So that's one of the big advantages. Even though if you have large coherence time, even though the gates are relatively slower, but you win on number of total gates that you can apply. So long coherence time means that they don't forget the information for so long, like for many hours, compared to other platforms which forget that information within microseconds, right? That's a huge advantage. And then the other big advantage is the high connectivity. So I'll again motivate that in my talk later, but you need to, let's say for an algorithm, you need to do a gate between any qubit that you want between other qubit in a large computer, right? It might be trivial in a classical computer, but the connectivity depends on how you wire them in other platforms. But in trapped ions, because they're entangled through collective motional mode, you can hold any qubit in this, let's say, a huge chain and another qubit in a huge chain, and you can do a gate between them. So even though they are linear, doesn't mean that you can only interact. You can only make nearest neighbor interact with each other. You can make a gate between any two qubits in a single chain. So that's a huge advantage compared to other platforms, right? And in the end, they have high fidelity of local and remote quantum gates. I'll motivate that. But what it means by fidelity is like you have least amount of errors when you are trying to apply a gate. So that's one of the biggest pain point in today's implementations, is that you have huge errors when you're trying to do a quantum computation, and then the errors will basically negate your result or negate your advantage. So trapped ions have world record high fidelities. Let's say for single qubit fidelity, I don't know, it's like 7 nines, and then 2 qubit fidelity is 4 nines. So IonQ holds the world record of demonstrating the highest single qubit and 2 qubit fidelity. And again, other platforms, they're not even close by orders of magnitude. It's not like, okay, someone else is 99.97, but no, they're not even close by orders of magnitude. That's the reason why we think ions are best. The other platforms invest on, let's say, error correction to mitigate those hardware noise. And even after error correction, they cannot meet this good number. So these are our numbers without error correction, just based on like just hardware errors. So that's one of the reasons why we think trapped ions are great. Yeah. So hopefully I motivated you enough why ions are amazing. Let us jump into understanding more details about the hardware. Let's jump into each aspect of the hardware. What are the challenges? What are the pain points? What are the amazing things of trapped ions, right? So the first thing is choosing a favorable ion. So I'm showing a picture of periodic table here. So I have various elements that you can choose and ionize them and then make them a good candidate for trapped ions. So the elements highlighted in red here are the more favorable elements compared to others, mostly because they have a hydrogen-like structure once you ionize them. So it's people who are familiar with physics, it's easier to deal with. The theory is easier compared to, let's say, other elements. So that's the nice thing. And then you need to have the energy levels that are more accessible using commercial lasers. So you cannot have, so we use various laser beams to control these ions, right? So you need to have the energy levels should be such that the lasers that we use need to be commercially available. They should not be in like deep UV or like very high IR. They should be close to visible that makes them like a good candidate for quantum computing. And then they should also have multiple qubit encoding. So I'll be talking about that, but if you have multiple qubit encodings within a single qubit, you can do lots of tricks. And in the end, right, like you need to meet those 5 criteria, and then there are inherent problems. Choosing an ion that where you can do, let's say, a lot of natural tricks would be the best platform to do quantum computing, right? Because we cannot manufacture these ions, you cannot change their properties compared to, let's say, other platforms, superconducting or whatever. You can change their properties and then do different things. But with ions, you're stuck with what nature gives you. So you need to choose the correct ion wisely. So the element that we chose is barium. Barium is nice inherent, like inert metal. I mean, even though it's very reactive, but it's more or less inert in vacuum. So we choose barium due to various properties, as I said, like lots of all the wavelengths that are involved in addressing barium atoms are in visible range. So you can buy commercial lasers, you can miniaturize them really well. It's in the end, quantum computing is hard, so we try to rely on technologies that are already really well established, right? Whether it is nanofabrication or, let's say, optical engineering or lasers or anything, you need to rely on some technology that is really well developed. So those kind of choices make us choose this specific ion, barium. Okay. Right. So let's start with like how we load these ions into a trap. So what you do is you take a piece of metal, right? Like the 2 mm purple color piece here. So you shine it with a powerful laser, which basically blasts the surface. So what it does is you focus like a really powerful laser onto a surface and just basically blast the surface and throws a bunch of atoms into the air. And the temperature of that blast is so high that it's higher than the surface of the sun. So it's like very hot, right? So the atoms basically get plunged out of the target, and then you get a plume in various directions. And some atoms, let's say, travel towards the trap. And what you do is you then again blast another laser onto these neutral atoms, which basically kicks an electron out of their valence shell and basically ionizing them. Once you ionize, then you create a bunch of potentials that catch hold of these atoms and trap them. So that's how you create these atoms. And you can do it on demand, as in you need one, you just create in a second. That's it. You got a qubit. Compared to, you don't need to go through levels of fabrication or whatever. You need to do this often because you do lose them. I'll talk about that later. But it's very easy to create a qubit out of it, right? So, and then you apply various static and oscillating potentials on your trap. And I'm not going into detail of like how these traps look like. I think part of this hackathon was to simulate how these traps work, but basically giving like a very vague explanation. You create various static and oscillating potentials using these various electrodes on a chip, which creates this oscillating confining potential. So this animation shows a blob here, which is like an ion. It is confined within these oscillating potentials. Because of laws of physics, you cannot use static potentials to confine a charge in all directions. So like Earnshaw's theorem prevents you from doing that. So what you do is you create oscillating potentials to sort of trap the atom within a specific region. And there are various traps, Paul and Penning traps, that have been there from, I don't know, 1950s. The specific traps that we work with are chip traps, mostly because you can fabricate them on a surface. You can use commercial nanofabrication facilities to create really precise electrodes. And that's one of the challenges with trapped ions, is that when you try to scale with large number of qubits, you need to create like lots of these electrodes. The electric field should not be interfering with each other, and so on, so on. So, but I mean, we have perfected it at HardHaQ. Okay, so once you create the atoms, ionize them, and trap them using these electrodes, the next step is you need to house the whole thing in a vacuum chamber. So in atmosphere, even though you trap these atoms in an electric potential, atmospheric environment has like a lot of stray particles that can go and collide these ions and basically either kick them off the trap, or you lose the quantum information. So you don't want any background collisions from the atmosphere. To do that, you need to house them inside a vacuum chamber. And the vacuum inside that has to be like almost perfect, like better than outer space, like orders of magnitude better than outer space. So we typically get 10 to the minus 12 or 10 to the minus, I don't know, sometimes even 10 to the minus 14 millibars of pressure inside this chamber. So it's like 14 orders of magnitude lower than atmosphere. So it's not very trivial to do this. And it's so empty in that chamber that usually you quantify vacuum based on, let's say, mean free path. Mean free path is how long a particle needs to travel before it collides the other particle. So mean free path in, let's say, in atmosphere could be very little, but the mean free path inside a vacuum chamber that we use is so high that a particle needs to travel almost across the globe before it meets other particles. So there's like really empty. Though in atmosphere, it's like few micrometers, I think so. So you usually have lots of collisions in air. You have like no collisions in this vacuum chamber. So that makes these ions really like they don't like any collisions. So you need to take away all the material out of this. And there's so much engineering involved in dealing with the materials, like what kind of pumps you use, how you fabricate them. It's like again, I can talk for hours how that can be done. But again, HardHaQ has perfected it. So typically in industry, vacuum chambers, or even other companies like Quantinuum, which are our competitors, the vacuum chambers look like the ones on the right. Usually they're like huge, many meters, bulky. They have lots of pumps. But HardHaQ over the years have miniaturized the whole thing. And this is a picture of one of our traps. And I'm keeping like I put like a deck of cards next to it for size comparison. So you can see that this is our whole vacuum chamber with the trap and everything. So what it has is, let's say, a trap, and then you have the atomic source to create these ions inside. And then you have various optical windows that are used to shine, like send lasers. So ions will be typically trapped in the center here, like where I'm pointing. And then you have various optical windows on all sides to send laser beams that can address them. And the top window, the big one, is what is used to measure these atoms. So it's like for trapped ions, measurement is basically looking at them because they fluoresce. So measurement is basically collecting the fluorescence from these ions and then understanding what it is. So you need to have really good access to solve that measurement problem. So you have a huge window on the top. Typically, I don't know, for optical engineers in the audience, we have more than, let's say, 0.6 Na numerical aperture to these ions, so that you can really collect all the individual photons from these ions. Okay, yeah. So this compact factor also makes the whole system like smaller, as well as like stable overall. Yeah, so that's one big challenge that, of course, IonQ has solved already. And the second, okay, so till now we understood how to trap these ions, how to create these ions, trap them, and then put them inside a vacuum chamber. But I haven't talked about, well, like, what the hell is the qubit inside the ion, right? Like, and you cannot use like an atom by itself as a qubit. So what you do is you encode two of the energy levels that these ions have as a qubit. So atoms have various energy levels, right? Like, I don't know, you would have studied in chemistry. Atoms have various energy levels, and you can use any two of these energy levels as a qubit. So qubit needs two levels, right? But it's important to remember that there are more than two, and often all your operations need to consider that they can go out of the basis. So you need to always bring them back, right? So yeah, so there are various reasons why we choose these two levels. So we choose the ground state hyperfine levels of a barium atom as two levels of a qubit. They're so stable that it takes years for them to mix between each other. So let's say I created a qubit in the 0 state, it will not decay to 1 state for, I don't know, no one ever measured. So it will never decay from 0 to 1. So they're both really stable compared to, again, other platforms where a stray field can just knock them off and then switch them between 0 to 1 or whatever. So that's very important. So the qubit we chose, the energy level between them is about 10 gigahertz. So that's why it's like in microwave regime. That is one of the advantages that we have. Yeah, so that's about it for the qubit encoding. If you're not familiar with qubits or quantum computers, it's often nice to visualize them as a vector on a sphere, on a fictitious sphere called a Bloch sphere, where the north and south poles here represent, let's say, 0 and 1, like product state. And the superposition is basically that the qubit can be anywhere on the surface. And as long as you're like, all the single qubit or 2 qubit gates is basically rotating that vector to a new position. And if you measure them, it will immediately collapse to either the north pole or the south pole, which is 0 or 1. So that's a nice piece of visualization you can use to understand how qubits work. And it's very important. Many people have a misconception that there is a physical sphere. There's no physical sphere. It's just a tool to understand how qubits work, right? So that's about it for the single qubit gate, single qubits. But as I said, one of the nice features that one needs to have in trapped ions, or like on an ion you choose, is you need to have multiple qubit encodings. So we have something called an OMG, optical metastable and ground qubit encoding. So it's famously called OMG in the field. So what it means is you don't just have a single encoding of qubit. So for example, I talked about the ground state encoding. You can also choose two other levels in the same atom, and you can call it, oh, this is my qubit. And you can also always swap between that and this encoding, between all these three. So you could ask, like, why is it needed? You can do the cool tricks with them, like hiding the information from one place to other within a single qubit, within a single atom. So that makes it like a really cool platform to do it, because, for example, let's say you have multiple qubits and at some time you don't want them to interact. What you can do is you can take a qubit and put them in a different encoding, and they'll stop interacting with the others. And if you bring them back into the encoding that you want, it will start encoding. It will start interacting with the other qubits. So that's one of the cool things that you can do with the qubits, that like trapped ions. So it's not just these energy levels that you can use for qubits. The another degree of freedom that ions have is their collective motional modes. So this is an important, most important aspect of trapped ions is that they, even when they're in linear chain of ions in a single potential well, they act as bunch of coupled springs. So when you have coupled springs, I don't know if you have studied, coupled springs have eigen modes or like eigen normal modes. So for example, I'm showing an animation with 5 ions here, where the highest normal mode is where all the ions oscillate with each other. So when I excite this normal mode, oops, no matter how big your ion chain is, they'll oscillate together. And there are other normal modes. The second one is called a tilt mode, where the ions would like oscillate like a tilting in tilting fashion. And there are various other higher order modes. Like the last one is called a zigzag mode, where ions are like out of phase randomly. So the important thing of trapped ions is that all of these ions share a single mode. And let's say if I catch one ion and excite one of these normal modes, all the other ions also oscillate at the same normal mode. Why is this important? This is what we use to do the entangling operations. The common phonon mode is used to do the entangling operations between all these qubits. So you can choose any ion and another ion in the chain, and you can basically shake the whole chain with using these 2 ions and then create entanglement. So I'll be talking more detail I'll be talking about like entangling gates a little bit more in the later section. But yeah, it's very important that the motion of these ions are really sort of really good. So because we are dealing with the motion of these ions, they have to be really cold as well. So typically, if, as I said, like when we create these atoms, they are as hot as the surface of the sun, right? So it's like they are really hot. You can catch them and they'll just fly away. What you need to do is to confine them. You need to cool them to many like micro Kelvin. So it's like 10 to the minus 6 Kelvin, almost absolute zero. So again, people have wrong notion that you can use cryogenics to cool that, but it's really hard. What we do is we use laser cooling to cool these hot particles to let's say almost 0 Kelvin. So the temperatures I'm talking about is like 10 to the minus 6 Kelvin. Even like the best dilution refrigerators can only go to, I don't know, sub Kelvin. But what we can do is like 10 to the minus 6 Kelvin, which is like almost zero, like zero temperature. So what you do is there are various kinds of laser cooling. One of the primary and easy to understand one is called Doppler cooling. So to understand Doppler cooling, it's almost like an optical brake. So you're breaking these atoms so that you can stop. So hot means they are basically moving at really high temperature, at really high velocities, right? Like they're just moving around. What you do is, let's say if you have an ion that is like moving in this direction, you shoot that ion with a laser pulse. So the laser pulse is such that it is red detuned. So again, if you know your Doppler effect, if you have red detuned, then an ion that is moving towards the laser pulse will see it as a Doppler shift and then and absorb the so it's like red detuned from the resonance of these ions. So if an ion is moving towards the laser beam, then it will be blue shifted and then it will absorb the photon. And immediately after it absorbs, it gets like a kick. So even though photons are like very light, I mean, no mass, ions get a momentum kick. It's very little, but you do that like many times so that it eventually the ion gets like slowed down in the direction. But you can say that, okay, but ion also emits it back. Then it also gets like the kick on the other direction. So what happens is when the ion emits the photon back, it emits in all the different directions, like spontaneously, and the average effect makes it zero. So in the end, the ion is cooled in this direction. And because the ion is confined in the electric potential, you basically, let's say, reduce the velocity in all 6 directions, sort of. So that's how you cool the ions using laser cooling. So basically, you shoot them with lasers. These ions absorb them and then emit the photon back, and then they get a kick. And this can be done so well that you can cool these ions to about like millikelvin, about like 10 to the minus 3, 10 to the minus 4 Kelvin. So it's like really cool. You cannot do that with any cryogenics. So that's one of the advantages of trapped ions, is that you can use laser cooling compared to, let's say, superconducting qubits. You need to do, let's say, you need to have like really cold cryogenic environments, like huge dilution refrigerators. Ions don't need to have, right? That's why our trap is like so little. So that's how you cool these ions to subdroplet temperature, like to like sub-Kelvin temperatures, right? So far, again, quick break. So far, we understood how to catch these ions, how to isolate them in vacuum, and how to, let's say, cool them, and how to encode qubits into these ions. So, any questions so far? Sure.
One thing behind the and are intrinsically quantum.
Right.
What do you mean by
So the energy levels that you have, like they, what do you mean? So are you familiar with like okay, sorry, I need to summarize the question, right? So the question is, what do I mean by what ions are inherently quantum, right? Like, what does it mean by that? So how do I explain? So the ions are so little that the effects of things like superposition or entanglement is you can immediately see them. So when you take like particles like I don't know, this water bottle or something, you cannot see quantum phenomenon in them because they are like they're huge. So ions inherently exhibit quantum mechanical properties. You don't need to like create quantum mechanical property in them. For example, I'll do a comparison, right? So do you know how superconducting circuits work? Okay, sorry. So what they do is they fabricate a system that that tries to show quantum mechanical phenomena. So the reason why we don't see quantum mechanical phenomenon in day-to-day lives is because uh, they're how do I say? There are various effects that sort of kill their quantum mechanical properties, so that there is huge error. But when you catch hold of ion, it's inherently a quantum particle. Uh, yeah, I think. Does it make sense?
so what that all creating?
Right. So it's, yes. So, I mean, you have quantum effects everywhere. You need to be able to isolate them and specifically look at these quantum mechanical phenomena, or else they decohere, or like you sort of, as the systems become big, you lose those effects. You cannot see them. Yeah. So other platforms sort of try to manufacture something that can show a quantum mechanical phenomenon, but ions inherently have that property. Go ahead. Right. Okay. This jumps into atomic physics. So the fraction is, so that is just a number. Are you familiar with like various quantum numbers? Like, it's basically a representation of showing an angular momentum. So it's a spin half particle. It's atomic physics representation. So it's like the subscript on the left shows 2 times spin plus 1, and the big letter S shows the L angular momentum, and then the subscript on the bottom right shows the J, which is the spin and orbit angular momentum combined. So that is just a atomic physics notation. Oh, okay. Good point. So this is magnetic, another quantum number. It's just, yeah, it's just another quantum number. You can think of it as like there is no significance of, I mean, or there is significance. It's just a notation. Go ahead.
Since we want the energy states to be stable.
Right.
So what determines whether a state is stable?
Right. So let's say the coherence time is one of the properties that you quantify with. So what you do is, let's say you create a superposition state between, let's say, these two states. Let's say you chose two states, and then you created a superposition state. So it's like, and superposition state is very finicky, like that can be destroyed through external disturbances. So the stability means that superposition state should not be destroyed for a really long time, because that inherent quantum phenomenon is what is used for the quantum algorithm. So if I told, right, like the biggest problem is the measurement. The reason why you cannot observe quantum mechanical phenomenon is that lot of errors do the measurement. So as I said, immediately you measure them, they collapse into 0 or 1, right? So let's say someone is continuously measuring them, continuously looking at them, then you don't have any quantum mechanical phenomena. It feels weird if you're not familiar with quantum physics, but that's what like if they're isolated, that no one is looking at them in some sense, that makes them stable. Go ahead.
Speaking of like that being isolated, any disturbing them at all kind of be a measurement for the collapse. How do you, how is it that sort of when they're all dependent on each other, vibrating in their own different modes, so you manipulate one sort of vibrates and so, or when you like bombard them with photons to slow them down, how does that, are those like also measurements?
Oh, a wonderful point. Yes. So you do that before you start your quantum algorithm. Yeah. So you do them like, that's fine. Yeah. If the quantum information is destroyed when you're cooling, but once you cool them, then they're cooled. Then you start your algorithm. Yeah. 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 Cooling destroys the quantum information in them. Okay. Any more questions? Okay, go ahead. Yeah. So again, good point. It is not continuous in the sense that you don't do cooling during the quantum computation, but you cannot keep these ions, they keep getting hot. So what you do is, as soon as you finish your quantum algorithm, you cool them again. So that's one of the, let's say, error mechanisms that you have, right? Like if they keep getting hot during your quantum algorithm, then you're sort of losing information. But there are so many clever tricks that people do. So what they do is they assign some qubits as the coolant qubits and some qubits as the information qubits. You can cool the coolant qubits because you don't care the information inside them. Cooling only few of the ions in a chain also cools the whole chain, right? So you can only cool some while you use others for the quantum information. So yeah, there are lots of clever tricks you can do, but there is again like a limit how well you can do it. Yeah. Because we use these motion to mediate the entanglement. So I'll cover that, like I'll talk about that. So it's basically, are you familiar with entanglement? I forgot how familiar, what? Right. So to entangle any two particles, you need to have a sort of shared state. So the shared state between all these qubits is the phonon, which is the motional quanta. So we don't encode our qubits into the motional quanta, but if you want to entangle them, what you do is you use that shared motional bus, right? Like I'll explain. I think you'll understand more in a bit. But yeah, so to use them for the entanglement, you need to keep them really cold. But also to a certain limit, you don't want them to just escape from the trap. That's also a reason, but you want it to be really cold to create the entanglement. I mean, even other, let's say, platforms like superconducting qubits, you need to cool them really well. So hotter they get, more measurements, like sort of more measurements happen in the background, and then they lose the information also. So there are various orders of effect, but the most important thing is the requirement to create the entanglement. Okay, cool. Any more questions? I'm not looking at online. Are there any? Is there anyone online? Any questions? Okay, cool. Perfect. Okay, so yeah, we understood double cooling. We understood how to encode these qubits into ions and then so on, right? Okay, so now let's understand how do you manipulate them, right? So till now, we only created the qubits. They are of no use if you cannot manipulate them and do various gates or measurement or anything, right? Like they're till now, this has been, let's say, just trapping the ions and cooling them was done in 1900s, or 30, 40 years ago. So that's nothing new. There's nothing new. Like you might have wondered, like, okay, ion traps may be used for quantum computing, but they're actually used in so many different places. Ion traps are used in, let's say, mass spectrometers. So if you go to, let's say, have you been checked, like swabbed in an airport, right? Like if they take a swab and they quickly check if you have any drugs. That works. The machine uses an ion trap to find out what kind of material it is. So there are like trapped. Even if you want to, let's say, if you take like a random substance and want to find what it is, you basically put that in a mass spectrometer to find out its mass and its properties. And the working principles of mass spectrometers is very similar to ion traps. So ion traps are not new in the field. They are like really used in like so many different applications, right? But what makes an ion trap a quantum computer is the ability to manipulate the qubits inside them. So a typical quantum algorithm looks something like this. This is like a really simplified circuit. So a quantum algorithm is typically called a quantum circuit. Uh, Contains various, like you start with various qubits. So the horizontal lines here represents qubits, sort of. So you have 4 qubits in the circuit. So you start them by initializing them to the 0 state. So you initialize all of them to the 0 state so that you know that where you're starting from. If you don't do that, then they can be in some random state, and then when you apply a gate or whatever, you basically get something random junk. So you should be able to initialize them, right? Like that is one of the criteria of making a good quantum computer. So you should initialize them to 0, and then you apply various single qubit and 2 qubit gates. So these square boxes represent a logic gate, very similar to a classical logic gate, right? Like you have and or. So single boxes represent like a single qubit gate where it only sort of manipulates a single qubit. But most importantly, the algorithm is built with bunch of 2 qubit gates, which is basically a gate that creates the entanglement. So before, when they are only prepared into 0, 0, they are not entangled. You need to create various kinds of entanglement between these qubits to be able to do the quantum algorithm. So, and in the end, you measure all of them to get the answer. So you do some kind of measurement depending on the platform and get the answer to basically complete the circuit. So what I'll do is I'll go through one by one to understand how we can implement that in trapped ions. Right, how am I doing on time? Okay, have half an hour more. Okay, good. I'm good. Yeah. Okay, cool. Yeah, so you have initialize, do bunch of gates, and then measure, right? So what you do for initialization. So remember the picture like this. This is bunch of energy levels where the ions can be, and then we encode these two hyperfine levels as 0 and 1, right? So what you do is to initialize them, you basically just shine a laser, a global laser, which addresses all these ions. So what it does is, uh, it takes the ions in the one state or the ions in out of the basis. So as I said, ions could fall out of 0 and 1, and then you're in like some other 2 or 3 or whatever. You don't want them to be within, you want them to be within 0 or 1 all the time, right? So what it does is it basically shines the laser. We basically shine laser to excite these atoms to a short-lived state, which is the P state, and then it just de-excites into the 0 state, which is where you're initializing them. So you can do this with really high probability. I don't know, many nines that you can like with high probability initialize them into 0. So it's one of the criteria for quantum computing. So it's a very simple process. You just shine on everything and then they fall to 0. So that's good. The measurement process, so I jumped to the last step, is also very similar. You again shine a global laser beam onto all of these ions. And if an ion collapses to upstate, it fluoresces, so it's bright. And if it is in 0, it is dark, so it doesn't emit any light. So what happens is you can collect all this light onto a camera or camera kind of device, and you basically look at the fluorescence. So if you remember the picture I showed in the beginning where you have like a chain of like many blobs, that is the fluorescence from individual ion. So if it is bright, you call them 1. If it is dark, you can call them 0. So you get the measurement. But under the hood, what you do is you collect the photons and then create a histogram like something like this. And for if it is in 0 state, it is highly probable that your collected light is in like you don't collect any photons. And if it is in 1, there is a high probability that you can collect like more than 1 photon. So you sort of, what does camera do is like it can detect, let's say when we shine this laser, it can detect the photons and then say, okay, your answer was 1 or your answer is 0, right? Yeah, that's how you do the measurement. Very similar to the pumping. And then comes the interesting part, the single qubit gates. So as I said, one of the important operation that you do on a quantum computer is the single qubit and 2 qubit gates. So what we do is you shine a bunch of laser beams on them. So what we have is we have ability to individually address these ions. So even though these ions are just 3 to 4 micrometers apart, right? They're very close to each other. We can still focus various laser beams. And by controlling the phase, amplitude, timing, you can rotate these qubits on a Bloch sphere to anywhere, literally anywhere. That is basically the qubit, single qubit gate. Yeah, so that's basically how you do it. And then for 2 qubit gates, it's very similar. You instead of shining the ions with a single laser beam, you shine 2 different ions with their own individually addressed beams. So this is a complicated phenomenon to understand. So these gates are called like Mormon-Sorensen gates. That's what we use to create entanglement between them. So I'll give a very vague, like a physical intuition of how they work. So what you do is the lasers, the photons in these lasers impart momentum on them. So they also like shift these ions a little bit and also change their state. And remember that the motion is entangled between all these ions. So they share a common motion. So when you like sort of tickle one ion, the other ions also get tickled. So what you do is you shine another laser beam. So first laser beam entangles the ion state with the motion. And the second laser beam also entangles the ion with its motion. So the ion's qubit is entangled with the phonon, and the second ion's qubit is also entangled with the phonon. And at some specific conditions that you do with the like laser pulse, like timing and then shaping, what you do is in the end, you disentangle the phonon from the picture, leaving both qubits entangled. So you can create them in a perfectly entangled state where if you measure one, the other state also collapses to the same state, or like they are highly correlated, right? So if you did not understand how this works, basically we catch two ions in a chain with laser beams and shake the whole chain and they get entangled. That's basically it. It's a hard process. And getting this with high fidelity is what makes a quantum computer a really good like quantum computer to solve hard problems, right? So how you physically do it, this is an animation showing a cartoon, right? Like you have a chain of 38 ions in one of our systems, and then you have a acousto-optic deflector. It's called an AOD. What it does is, based on an RF signal, it deflects the light by ever so little that you want. You can control them really well. And by doing like precise beam shaping and optical engineering, you can sort of steer these laser beam anywhere you want, and then you can basically address any ion you want, right? So if let's say I want to entangle two ions, let's say ion 4 and then ion 24, I can shine two laser beams on ion 4 and 24, and then you can get them entangled. So so this is very scalable, as in I can make these ion chains really long, but I can the deflector, a single deflector can be used to address I don't know, hundreds of ions, not hundreds, but about 50 to 100 ions. But the problem is, as you keep increasing the chain length, they sort of the fidelity, which is the metric of like how good these operations are, like falls. So you cannot do really well as you create like really long chains. So that creates a obvious hurdle for scalability, right? So the largest ion chains you could do so far, I don't know, range from like 50 to 100. If you go longer than that, then they sort of they lose their stability. You need to various stray electric fields kick them out of the trap and so on. So you have so many errors. So that sort of jumps me into the next topic is scaling. Like how do we scale these trapped ion quantum computers to actually do like amazing problems? So before going to the next section, any questions? Go ahead.
Setup. So we do the measurement, like what kind of camera we use.
So it's called a QCMOS. It's a CMOS camera, but which has a really high quantum efficiency. So normal cameras have huge background counts. As in, let's say if you don't have any light, they still detect like errors, right? Like you have noise from the electronics that thinks that okay, there is a photon. But there are special cameras which have very low noise. Again, they're commercially available. Again, mostly made for quantum computing. They can detect very weak signals of the order of like many photons. And there are like photomultiplier tubes. There are superconducting nanowire single photon detectors. So there are like various different kind of detectors. So based on your application and scaling, you use them.
Yeah, the quick question with the setup for the entanglement.
Right.
What's this laser you use?
So this specific barium that we use a 532 nanometer pulse laser. Why pulse laser? There's a reason behind it, but yeah, they are like high power, typically couple of watts of power for each beam. Yeah.
The size stages with the beam up.
Oh yeah, that is one of the engineering challenges that the field has solved over many years. Like you need to focus them down to like few micrometers, and the challenge is that light should not leak into the other ion. So let's say if I want to address, let's say ion number 2, the light should not leak onto the other ion, so that it will basically it decoheres the other ion. So The challenge is that you need to basically just focus on one and then not disturb the other. So it's again, if you know optical engineering, it's quite challenging, but we have solved it. Any other? Okay, go ahead.
Like distinguish different particles for entanglement. So like you're shooting visual beams to that you want to specifically entangle. And so is it like it's like the states like certain type of fine structures that it like the photon path is introduced for the laser? Like how like I thought like I'm sorry this
Go ahead, go ahead.
from what I understand, I thought that like all of these ions have the ability to emit a phonon.
Right.
So it's just that you're shooting those specific ones and they get enough energy to go in that phonon path to them.
Oh, they don't emit a phonon. They are in they share a phonon. So phonons are a collective property. It is not just a property of single atom. So they can emit photons, but not a phonon. See, phonon is basically like motion, right? Like, so because they are all charged, each ion cannot move independent of others. So if you move one ion, everything else moves. So they share a common phonon. That's the nice thing. You don't. That's what. So let's say if I shake one, everything else shakes. So it's like I created a phonon that everyone share. And now the qubit state. So qubit is a property of the individual atoms, but the phonon is shared. So what you do is you entangle the qubit with the phonon. So you sort of you're sending the information from this common bus. So yeah, people call it a phonon bus because it is shared between all of them. So you entangle the state with the phonon, and because the phonon is also entangled with the other qubit, and you entangle the qubit with the phonon, and then you take the phonon away from the picture, it leaves both the qubits entangled. It's a vague understanding. It's quite complicated what's going on, but that's the idea. Cool. Okay. Yeah, so obviously the next question is, okay, you have this chain of ions. How do you scale them? How do you make like millions of qubits, right? To make it a good quantum computer, you should be able to like scale them to large number of qubits. So the first thing that I would like to highlight is it's not just the number of qubits that matter, it's how well they are connected. So let's say you have 20 qubits in different platforms, right? I'm showing examples of like IBM, Google, and Rigetti, other companies. Usually they're manufactured and they're wired on a chip, right? So a qubit can only talk to other qubit that has a connection, right? Let's say you take this qubit and then it can only talk to the qubit next to it because of it has an edge between it. But let's say if you want to perform a gate between, let's say 1 and then let's say the last qubit, what it needs to do is it needs to talk to this qubit, and this qubit will talk to the other qubit, and then you need to go through you need to jump so many loops to get from one to the other, right? If you want to do a gate. Similarly, let's say other platforms, but trap brands have this intrinsic all-to-all connectivity, as in I can catch one and connect any one in a single step. So that gives a huge speed up and complexity advantage compared to other platforms. So the reason why I'm saying is it's not just number of qubits matter, that it's the complexity that matters. And a 20 qubit machine using trap brands could be more powerful than like a 50 or 60 qubit machine in other platforms, both because of high fidelity gates as well as connectivity. So that's one of the so it's important to know that it's not just the number of qubits, it's the complexity that is important. But okay, let's compare within our platform. So how do we go even beyond, let's say 30, 40, or current chains are like 50 or 60. So the next thing is I told, right, like the problem is you cannot make them arbitrarily long. You cannot create a chain of 1,000 ions and still have the same high fidelity operations. So what we do is we then split them into small parcels. So we call them a parcel of like let's say 30 ions. you can create many of these parcels adjacent to each other. So each parcel, you will be able to connect any of the ions within the parcel. But if you want to connect an ion from one parcel to the other, you just basically bring them together, merge, so they form a single chain, and then you can create an entanglement because they share a common phonon bus. So once the operation is done, you can just split them back and then continue. So this way, you still have the all-to-all connectivity, but from one qubit to the other qubit, you might need to jump, let's say, 3 steps or 2 steps to connect from any qubit to other qubit. So this is one of the ways that we solve our, like, let's say, scaling strategy, right? Like, but even then, how many parcels can you create? Like, can you create thousands of these? It's very hard to manage them. You need to move them around. You need to have various laser beams. The whole thing becomes really complex. You need to have like lots of optics, shining laser beams to all these ions, right? Like, it becomes a nightmare. So that's why we move to a new technology through which we call it as like electronic qubit control. So instead of lasers, we use RF antennas that are like engraved within the same chip. And you could use those, you can use the field from these RF antennas to do the gates like you want. So this mitigates the issue of shooting a laser beam from outside. You can sort of pattern these waveguides onto the chip and then create entanglement. And then basically you can, I'll just skip this slide, but you can have a huge chip with many of these patterns written onto this waveguide. And then they can share these common drive and still be able to do the gates. So this way you can, let's say I have a chip with, let's say, hundreds of ions. I can parallelly do a gate on all of them at a time. That's one of the big advantages that we have compared to other platforms. So, so this is the implement. So this is not just in fiction. We have implemented this, and our world record fidelities is with a system that uses waveguides that are written onto the chip. So we are in path of like scaling them further to I don't know, hundreds of thousands of qubits. So the question now is like, okay, how many can you put in a chip, right? Like maybe 100,000, 200,000. Like, so after that, you will start creating so many problems because there are like so many wires going on. There is crosstalk issues and everything. So taking the analogy of, let's say, classical computer, you have a single CPU which has some capacity of compute, but after that you can only make a single CPU so big. After that, you need to connect multiple of them, and like, let's say if you want to make a high performance cluster, you need to put them in a data center and then connect them through I don't know, Ethernet or whatever, right? Like they need to connect with each other to implement even more powerful algorithms. So there is an analogy with even in trapped ions. Again, another advantage that we have compared to other platforms is that we can connect multiple of these chips together using photonic channels through various switches and then entangle them. So you can choose an ion in one trap and an ion in other trap somewhere else that is connected through these photonic channels. So what you do is you entangle the ion with a photon, and then you entangle the other ion with another photon, and then entangle these photons together, which creates an entanglement between an ion in one trap with an ion in other trap. So you can basically connect and make a huge cluster out of this. Yeah, so there's some physics of I'll skip, but let me know if you're interested in hearing. But so in basically you can scale this whole thing into a data center level where you can have various racks of quantum computers connected to each other and also doing quantum algorithms between them. So again, compared to other platforms, there is other platforms that don't even have any solution to do that. They have to put everything in on a single chip. There is no way they can connect between multiple quantum computers. But again, trapped ions have a way to connect them together. Yeah, so I'll end my talk by showing this slide again. This advantage of being able to connect these quantum computers through photonic channels makes them a best candidate to be in the whole quantum networking ecosystem. You can connect these quantum computers over quantum internet, and get them like connected and doing you can do like complicated algorithms over quantum internet. Yeah, so in conclusion, we borrow like perfect identical qubits from the universe and make complex calculations. And IonQ's approach meets and exceeds the DiVincenzo's criteria and offers high fidelity gates and amazing coherence. And as I said, quantum computing is one of the humanity's most difficult and precise engineering challenges, combining physics and extreme control, right? Like there are problems that needs to be solved by physicists, chemists, mathematicians, optical, electrical, mechanical engineers, and even nanotechnology and computer science. So there are like expertise from so many different fields that go into making a good quantum computer. And this is the time where we are going through a big revolution of like building these. And yeah, if you're interested in like being part of this amazing revolution, like consider joining us. Thank you. Questions? Yeah, go ahead.
Say you know, have like one chip, both of the chips are separate in that environments, and then the photonic wave is just a fiber optic.
Yeah.
So is HardHaQ, I don't know if I'm allowed to say this or it's proprietary or something. So like, are you guys actually working on the interface of ion to the photonic wave to send quantum information?
Yeah, we already demonstrated and it's public. Yeah, we already have that. We have two for like trapline systems that are connected through a photonic link. Yes. I mean, we have showed entanglement, everything. Usually the errors are, sure, the errors could be because of the environmental fluctuations, but you can sort of use smart tricks on these fibers, like the environment. You cannot just take a fiber and then leave it in the air. You can sort of house them in really good environment and then avoid those fluctuations. So I think the industry best fidelity between, let's say, ion and ion through this photonic channel is about 97%. I mean, we are there, but we are, again, it's not public of how much we have. We are working towards reducing that. But yeah, the fidelity between remote gates is definitely a bottleneck compared to fidelity within the same system. So that's why you don't want to, let's say, so that decides the architecture. Like you don't want to just connect every qubit with the other qubit. You want to make your local qubits really well. And then you also sometimes use the remote connections, right? Similar to, again, in classical computing, right? The gates between, or like the operations within a CPU is much faster and then much more performant compared to, let's say, in a cluster, right? So that's why you divide your algorithm such that it takes that advantage of, let's say, dividing your whole problem into small chunks where you're only sometimes communicating between CPUs. So yes, there's similar analogy here. Yeah. Next question. Yeah. Yes. So phonon means motion, right? You can just keep one particle, and if it moves, it's a phonon, right? Like phonon is a quanta of motion. So yeah, I think that's my answer. I think it's like phonon is, you need, I mean, there is a misconception that you need a medium to have phonons, is because you need something to move, right? Like the movement is the phonon and the particle itself is moving there. So it's physically like shaking a little bit, very, very tiny movement. So it's like the amplitude of the motion is like several nanometers, but that's enough to create a quanta of motion. I hope that answers. Go ahead.
So you mentioned that it's very important for us to have connected qubits.
Right.
So what does it mean? Okay. That's a good one.
So connected means you should be able to do a 2-qubit gate between those 2 qubits. So let's say if I don't have a connection, that means I cannot do a 2-qubit gate between, let's say, 1 and like between I and J. Then they are not connected. If you can do a 2-qubit gate, then they're connected. Yeah, go ahead.
Question. Saying like you have one trapped ion chip, another chip, and optical fiber. How would you get from like the data encoded for the trapped ion bit to an optical signal, and then how would you convert back into trapped ion?
Right. Yeah, I skipped that. Sorry, in the interest of time. Yeah. So what you do is, so you have a chain of ions here, like shown by these blobs here. So you choose one qubit and call it an interconnect qubit. So what you do is you create these ions in a specific state and excite them to a short-lived state. What it does is from there, the ion decays into either 0 or 1. And when it decays, it emits a photon. And that photon is dependent on the state where it decays. So basically, if it decays to 0, it emits sigma plus polarization light. If it decays to 1, it emits a pi polarization light. And when you collect that into an optical fiber, you basically create an entanglement between the H, which is the horizontal polarization of light with the 0 state, and the vertical polarizations light with the 1 state. So this way you can create ion and photon entanglement. And then you do that on 2 different systems. So you have, let's say, one barium ion in one system and the other barium ion in other system. You make them simultaneously emit the photon, right? You apply your laser pulses such that they emit a photon at the same time. And what you do is you collect those photons and then interfere them on a beam splitter. So when you interfere them on a beam splitter and then do a measurement, a certain kind of measurement, like if the photons get entangled, you get a certain kind of measurement, and that measurement sort of in a Bell basis, that's what it's called, entangles the ions between these 2 qubits. Yeah, so you entangle the ion with a photon, and you entangle both photons together, sort of, which creates the ion-ion entanglement. Yeah. So this way, you also get all-to-all connectivity in some sense, right? Like, so I can choose any one chip and the other chip, and then if I route my optical switch properly, I can get a qubit from, like, a photon from one chip and the other chip, and then make them interfere. So it doesn't need to go through 10 different steps to entangle it. So that basically scales really well. Yeah, think of it as, again, classical network. You have a switch. If you have multiple computers, they first go to the switch and then go back to the other computer. So very similar analogy. Any further questions? Okay, all right. I guess you understand something. You understood something from this talk. Hopefully, it created more questions in your head to go and explore yourself. And feel free to, I think there are like so many online tutorials and resources to understand how trapped ions work. Even though trapped ions are like less explored, trapped ions, like the very first quantum logic gate was first implemented on trapped ions, like in 1995. Even though superconducting qubits catched up later, but trapped ions were the first quantum system that were used to create a quantum gate. So there is like plenty of literature online. So yeah, explore and then let me know if you have more questions. Thank you.
in the Center for Emerging Device Technologies. And you're staying here. Are you coming on?
I'm just gonna go.
You just want to leave? Okay. I would have come through here many, many years ago in both physics and then engineering physics, and I essentially haven't left. Right. So I've worked in different areas within McMaster University, initially as an accelerator type person, studying radiation damaging materials. and then now help run the clean room facility. And there are only 2 of us actually, and you'll see all our equipment as well, but it is quite a lot of equipment, and it's unfortunate that there's just 2 people. Sometimes it's too much, but we do get help from graduate students as well. So let's go into what is called a class 10,000 clean room facility, and you can tell me when you want to start recording if you haven't already.
Okay.
How many students missed this?
I think we had 2 that didn't show up.
Okay, and they're from Western as well?
One's from Waterloo.
Okay.
And then the other one's from.
You want to put your backpack down, you can.
Oh, sure.
It's on the floor. If you put it down on the floor, please don't hit your head on the pass-through, just behind you.
Oh.
Some people put it down on the floor just behind you,
Yeah.
and then when they stand up, they hit their head.
Yeah, that makes sense.
Okay, it's like hitting your head on the dryer in the washroom if you're drying your hands and you're tying your shoe at the same time. I did that once. I will never do it again. Okay. Yeah, and you can put your coat down there or on the cart as well. Probably shouldn't film the water bottle. This isn't in the lab yet. Okay, so you tell me when you want to start.
Yeah.
Okay. So welcome to the Center for Emerging Device Technologies, class 10,000 clean room. What does 10,000 mean in a cubic foot? No, it's not metric, it's a cubic foot, 10,000 particles. What kind of particles? Hair follicles, skin follicles. I'm not purposely spitting, but we do know even from COVID that there is spittle. And this is detrimental for the types of devices that we're making because we're working down at the micron level. So for those people who don't know what a micron level is, a typical hair is 50 to 100 microns. We ripped one of mine out and put it in the scanning electron microscope. It's 47, so it's a little bit thinner. And so the problem there is you don't want any of these things, dust gathering on your samples because you're doing different coatings and stuff like that. I'm losing my voice. Excuse me. Just gotta sit here. We are working at the 1, 2, 3, 5 micron level, making things like ridge waveguide lasers. So it used to be called the Center for Electrophotonic Materials and Devices. We mostly worked on 3-5 semiconductors, gallium arsenide, indium phosphide. Later on in the tour, we will look at our tour facilities in the Tandem Accelerator building where we have both electron beam epitaxy and MOCVD. And so we made things like ridge waveguide lasers. These are lasers made of 3-5 semiconductors, which you put electrodes on top, you get current out of them, and they're used for transmission of optical signals in fiber optics for the telecom industry. That was in the boom of telecom. So companies like Bell Northern Research, JDS Uniphase, we had a lot of collaboration with them. A lot of students ended up working there in Ottawa area, and for also smaller companies, a lot went to the United States, to Silicon Valley, mostly into California and things like that. And they're still working there, and I'll go through that when I show you where some of our students ended up as well. So a ridge waveguide laser would look something like this. This is an indium phosphide sample. When I showed it to someone, they actually dropped it, and it's very brittle. So this would be a 3 quantum well indium gallium arsenide layer on indium phosphide, and it lasers at 1.55 microns. That would be used for your telecom industry. But you could, as a designer, ask the grower to grow a different material structure to laser at a different wavelength. That could maybe be used as a glucose sensor, for example, in the blood. Or it could be used as a pollution sensor. If you know that a certain pollutant in the air, let's say in a hazardous situation, absorbs a certain wavelength of light, you could design a sensor, and you could actually get a MEMS robot, a flying robot, and we had a student working on that years ago. You could put a CCD camera on that little flying robot as well, plus a ridge waveguide laser sensor to see what hazardous chemicals are in that situation before sending firefighters in, for example. Right? So that was in the boom of semiconductor industry. Something like this could also be used as an optical sensor, right? Optical sensor for sensing strain in bridges. Be used as a photo detector as well. So we had to reinvent ourselves. How do we reinvent ourselves if we're not going to do just photonic materials? Well, anything renewable energy, solar cells. So we have, for example, silicon solar cells. The undergraduate labs in 4th year make a silicon solar cell. So they start off with silicon. You can take a look at that. In this case, it is a P-type silicon. It would have been doped with boron in the first place for the manufacturer. And then in some of these cases, I would have implanted the sample with an ion implanter, and we'll look at that over in the other building, the back side to make it more P+, and then to make the junction, the PN junction, I would have done phosphorus implants in the top layer. So here, the students pattern the samples, and they either use our facilities to do the patterning, or they have a very similar lab with what's called photolithography, and I'll talk about that in a few minutes, to pattern inverted pyramids in the silicon sample. The inverted pyramids will, as the light comes in, reflect and gather more light. So you're essentially capturing more of the solar spectrum of the solar simulator that you're shining onto your sample. And so these are different devices, different dimensions and things like that. And hopefully if you measure the solar efficiency of these, you would get a decent number. Right? But it depends on how you do your doping and whatnot. Some of them can be doped by ion implantation, as I said, but you can also do what's called spin-on dopants. So you have a borosilicate glass or a phosphorus-based glass, and then you would do diffusion type doping. So these are things that the students learn mostly in fourth year in a fourth-year lab. And I think there is a semiconductor manufacturing lab where they do that also in fourth year, and it's part of a 6th level grad course. So when we have to reinvent ourselves, how do we reinvent ourselves? Well, I talked a little bit about renewable energy, but nanowire solar cells. So do you see how dark that is and how black?
Yeah.
Okay. So that's harvesting light. So that is a gallium arsenide substrate with gallium arsenide nanowires on there. And that would have been produced here in the lab. So students would come in here, and it could have been on silicon as well, on 111 silicon. And what they do is they come and clean their samples here. They would etch the native oxide off. They would put down a nanometer of gold on the sample. They would take that sample then to the MBE lab, to the grower. The grower would put it in the load lock chamber and then the main chamber, anneal it at about 350 degrees C. The gold coalesces into balls, essentially. And then you would start your recipe for growing depending on what the person has asked you to do. So you might ask for just gallium arsenide, or you might ask for doped gallium arsenide, or you might ask for a PN junction or a PIN junction or whatever. So you could be studying the solar activity of this and efficiency of these nanowires. And so if you look at this scanning electron micrograph, this is one of the gallium arsenide nanowires. I don't know if you can see, but the gold wires are the gold dots are up top. And so what people were doing when they were studying this before is how much does the substrate contribute to the solar efficiency compared to the gold nanowires? So they would planarize this whole surface to cover the whole thing with a polymer, and then do reactive ion etching in this lab, go to the Reed Center for Electron Microscopy, which is a world-class microscopy facility on campus in the next building over, keep reactive ion etching and checking to see that they've exposed the gold, and then do their electrical contacts from the top, shine your solar cell onto usually you put indium tin oxide on the top as well, and then a contact on the bottom, so you could measure the solar efficiency of your solar cell. But we're talking about solar cells, but these could also be used for sensors. They could be used for biosensors. They could be used for sensors in smoke detectors and things like that. Now, the problem with this sample, in my opinion, is 2 people have touched it. You can see fingerprints in there. And I train even like public school, very young public school kids and then high school children. And I think that's who touched them. But the problem there is those people have gallium arsenide, arsenic nanowires in their fingers. And it's not like petting a cactus. But we don't know what the synergistic and long-term effects of nanowires are. That includes like from arsenic, which is a carcinogen, but also anything that's in makeup, sunscreens, it's titanium particles. Just like we didn't know the effects of asbestos in smoking and secondhand smoke, I think that's something that's going to come down the road. When you're talking about nanoparticles, putting silver nanoparticles into detergents as well to make them whiter, brighter, but then your laundry water goes into the lake and you eat the fish from the lake and that water gets recycled and that's your drinking water. And so those are things all from an environmental perspective and a health perspective that one has to think about, right, if that makes sense. Okay, so those are examples. And then what do we have? We have the mechanical engineers. And the mechanical engineers make devices like this. This is a microfluidic mixer. So this is just silicone. Silicone like the caulking around your your shower and your bathtub. And when they made this, about 15 years ago or so, this was a prototype, microfluidic mixer, 2 channels in, 1 channel out. They took a red dye, a blue dye. Does it mix? Does it become purple? Just like mixing Easter egg colors, things like that. But what they used, things like this, was they were working with pediatric doctors at the general hospital. And when a child is born prematurely at about 7 or 8 months, the lungs are not developed. Can you oxygenate the blood to help develop the lungs? And so they would take a microfluidic device like this from the umbilical cord, attach it in, and you'd have to test this out and see. Now, I'm actually not sure if they actually do it yet and have permission to do it on this, but they were working on piglets and rabbits at the time, right, with pediatric department at General Hospital here in Hamilton. So that's one example of other people who use our facilities to do microfluidic devices for medical applications. And we have something, this is just a prototype, but again, a microfluidic sorter. Different channels in, different channels out, different pipes, 2 electrodes, chromium electrodes, just on a glass slide. I mean, now they would make this more fancy. Think of even things like the COVID test. The SARS-CoV-2 test didn't exist before, right? And now you can put saliva in or body fluids, and you can measure something either electrochemically or by something also called ion-sensitive field effect transistors. But in this case, they were sorting worms, and I call them worms, but they're not worms. I didn't take biology, but C. elegans nematodes. C. elegans nematodes have a genome sequence that are 96% similar to human beings. And so if you were going to study neurotoxins on people, drug delivery on people, you would start with the nematodes first. And I believe in the past, people used to sort these by hand. They would pick the smaller ones and put them in Erlenmeyer fast, and the medium-sized ones are here, and the big ones are here. Just like different-sized people are affected differently by drugs and alcohol and things like that, it's the same with the nematodes. And you start, before you expose people to anything or have permission from the FDA or whatever to do that, you would start with nematodes first. Right? So this was an automatic sorter. You'd have smaller microfluidic channels. You'd put your electric field across this, sweep through so that the bigger ones would get through, the bigger channels. I mean, I suppose some small ones might get through. But you could sort nematodes, you could sort bacteria, you could sort viruses, you could sort drugs based on sort of this principle. Now, this already exists. It's much, what they have is much fancier than the prototypes that they made years ago, but this was sort of a starting point. And so I think what's happening now is a lot of effort is going into biomedical applications, lab on a chip, self-diagnosis. One of the reasons for that is it's difficult to get family doctors, it's difficult to get appointments with specialists, medical specialists in the field. It's difficult to get things analyzed and done in a timely manner. And so, for example, we have one lady professor, Dr. Leila Soleimani, who I believe has patented a device that will measure tuberculosis. So in developing countries, in the field, essentially, you can spit into a device similar to the COVID devices, and hopefully it's not false positive for tuberculosis, but then you can get to your nearest village or clinic in the nearest town. But you can self-diagnose in that respect if you think you're having symptoms of tuberculosis. Yes.
What's your rate of like false positives and false negatives?
That I don't know.
Okay.
I don't think it's too bad though. Okay. And there may be ways of distinguishing that between. Also, I think that has to be looked into as well.
Yeah.
So I'm not a bio person. I don't actually know. Because they would just do the devices here and then they'd run off and do their measurements elsewhere. Right? They're actually not even in this building per se. So, as you know, we have the COVID tests, but there are tests. What they're looking at now is things like for urinary tract infections. They're looking at electrochemical sensing and making similar types of devices. But they would use some of our equipment to put down the electrodes to make their transistors, their field effect transistors and stuff like that. So what they do, there are things called ion-sensitive field effect transistors, which are biosensors. Those are called ISFETs. And there you would have a source, a drain, a gate, and you would put whatever you're interested in on the gate, essentially, and you would measure the ID characteristics of that. And so that on the gate could be your blood sample or your urine sample, or it could be the antibodies or the proteins, and you could functionalize them as well. And again, this is more biology than I'm familiar with, but you could then know whether someone has a particular bacteria or a particular virus or a particular protein, if you had a heart attack or whatever. But I think in particular urinary tract infections is what they're looking at right now, at least some of these people are studying, because as the population ages, that is more common amongst both men and women. Right? And so if you can do a quick method of finding out what the issue is, rather than waiting for the bacteria to culture and waiting 3 or 4 days and you're in pain and you don't know what antibiotic you're supposed to take, but you know you have to probably take an antibiotic, it is problematic. And I think we're going that way too with our society. Lab-on-a-chip self-diagnosis. I mean, people have Apple phones and stuff like that right now, or Apple watches, I should say. To measure things, you can also measure some of these things. You know, are you sweating? Are you nervous? Are you stressed out? You know, what is happening, and should you report that then? Or is it important or not? Or you know, when should you start seeking help? I think you'll find that's the route our society is going. You know? So anything bio-related. So students come here and they learn to prepare their samples. They do something called photolithography. So the microfluidic people would use a mask like this, where they would put a photosensitive chemical on their sample. Their sample might be a piece of silicon, a piece of semiconductor, whatever, and there's a pattern on there, different channels, different microfluidic patterns and things like that. Or you could use a typical 4-inch square glass mask with a pattern on it. So if you take a look at something like this, and that's the difference. So these would be more expensive than this, but these are down at the micron level. This would be hundreds of microns. You can tell by the difference in size as well. Now, if people want to go to submicron, you would have to do either E-beam lithography, or you can do direct laser writing and things like that. So we have the equipment for doing that. We do not have E-beam lithography equipment though here at McMaster. Both Waterloo and U of T do. And I think we're trying to get that here, but these pieces of equipment are very expensive as well. Okay, so if you look at this sample, this is just a glass plate. What do you see if you look at this? It's actually a trick question, kind of. You can hold it if you want.
Oh, sure.
It's a trick question. I mean, it's very simple.
Yeah, it's just a bunch of squares. Right?
Yeah, a bunch of squares. Some are black, some are white, right?
Yeah.
But they mimic each other, right? And you see a line that runs horizontally between them. Is that correct?
Yeah.
Okay. What you don't see, because you can't see at a micron size feature, is the same color as the square is a 1 micron line running up and down between them. So it looks like this. And that is a shape of a bolometer. So we had a postdoctoral fellow years ago working on laser ablation of different stainless steel alloys. And at the time they wanted to know, this was femtosecond ablation, how much energy is deposited into that stainless steel and what was the pit that was blasted out essentially. So they would aim the femtosecond laser at that line in between the two, and it would ablate the material, and you'd be left with a hole essentially where you eroded away the material. But you would get a voltage gradient across the 2 electrodes, and that's a bolometer essentially. You're measuring temperature. You can measure the size of the hole. Right? You could do electron microscopy and do that, and you could come up with some analysis as to how much energy is needed to ablate certain types of stainless steel materials, and what the difference is between one stainless steel alloy and another. So those are some of the applications that people have used our facilities for in their research, either for the master's PhDs, or in this case, this was a postdoctoral fellow. Right? So in order to do patterning like this, we put a photosensitive chemical called photoresist. If it's a positive photoresist, where the light shines on it, UV light from the mask aligner, you cross-link the material, and that gets etched away because it's positive in the developer and gets removed. So you would get the positive pattern that you see. If you had a negative resist, it would be the opposite. It would cross-link, make it harder to be removed in the negative resist developer. And so we have masks that are both positive and negatives, and you can have photoresists that are positive and negatives depending on what you're trying to make. Right? So typically for the microfluidic devices, they work with negative photoresists. For other devices that we make, it's often the positive photoresist, but there's pros and cons for both. Are there any questions? So one of the questions that people ask is, why are there yellow lights here? Why is everything yellow in that room? Why are the lights yellow? So I talked about a photosensitive chemical. You only want the mask aligner, and that's the MJB3 with the piece of equipment with the orange base here, right here. You want only that UV light exposing your photoresist and not the UV component of the fluorescent lights, because that would then expose the whole sample. Right? So that's a way of ensuring, and the lights are not all in the clean room will be UV sleeved, or they would be lights that have a plastic coating on that. Usually it's a yellow coating that will stop and block the UV light from getting onto the sample. So students are taught to come in here and work with the equipment, work safely with the equipment, to try and do their research, to try and prepare their samples, to put down their metal contacts, to do, for example, their IV measurements, whether they're measuring solar cells or their nanowires, or making their microfluidic devices as well. And we'll look at more equipment that we have in other labs that support some of their research. So we want them to operate it safely and in a way that the equipment doesn't break, to recognize when the equipment fails, because if it fails, we have to fix it. And there's only 2 of us, and you'll see there's a lot of equipment that we're responsible for. So I prefer if people recognize when something goes wrong and then tell us, it's not quite working, could you please take a look at this? And they pitch in as well. I mean, we couldn't do it without their help as well. Okay. So if you'd like to step in, you stay on the right-hand side, or try to stay on the right-hand side of the bench in the change room. We'll just take a peek in the equipment and we'll go from there. So come on in. So, I mean, if this were industry, you wouldn't be coming in with shoes like this, street shoes. And I said it was a class 10,000 clean room. At Intel, they have even a class 1. So, you wouldn't come through with clothes. You would have air showers out there, and there'd be robots inside here if it's a class 1. But for what we want to do at the micron level or whatever, and usually it's tens of microns, class 10,000 is good enough for us. Under each of the hoods, it would be about a class 100, because we have what's called HEPA filter air, high efficiency particle air filters coming through, and they are filtered at 0.25 microns, and then the air blows through and goes out. In fancier clean rooms, the air would come down and it'd be blowing you in, and there would be air return lines in the floor. Essentially, you'd have perforated floors. So students come in here and they have to put the clean room gowns on. You put the hood on, you put a gown on. If this were industry, you would have to have beard coverings and stuff. We don't demand that because it is class 10,000 clean room, but no makeup, no mascara, no powder, no chewing gum, because that can be problematic as well. And people should gown up.
Moisturizer, would that be allowed?
Yeah, but anything that particles can fall off and stuff like that. Like mascara tends to be like that, and powdery. And I mean, I tell a story about there was a student in here once, and his samples, he was spinning photoresist, and it just didn't look good. And you could see it was dirty and splotches. And so I did the same. I used the same syringe and the same chemical photoresist that he used, and mine looked okay. And he went and repeated it, didn't look good. So we got new syringes and stuff, and mine were always okay, his were not. And then I noticed he was chewing gum, and you're not supposed to chew gum or eat candies in the clean room. And it's the spittle, and we know from COVID that when you even talk, I'm not purposely spitting, but there is spittle coming off. And, I mean, sometimes if you talk too exuberantly, you can see the spit on your sample, right? And you're putting a coating down. You're putting either photoresist down or an oxide layer that you're going to use as a layer for etching later on. It would be called a hard mask layer for making your patterns and stuff like that. So the students gown up. They hang their coats up here. We've gone to bags since during COVID times. We didn't know, was it okay to touch other people's gowns? I mean, certainly most people weren't in during COVID. Myself, I was here, and a colleague Sean, because we were working on different materials and supporting COVID research and people who needed our facilities to do some COVID research. And we also contributed any spare parts that I had, like spare supplies of masks and gloves and gowns and things like that to the hospitals around here. And we got our money back in the end. Yeah.
Was that for the COVID tests that you were doing research?
Mostly mask material and things like that, not so much the COVID test. But there were people working on COVID tests, but they had COVID tests by then. Right? That had been developed already, which was not, I mean, that's a good thing that they had though. Right? I mean, that had been the biochemists and the biologists and medical field people did know that. And they're still looking into other test for other diseases as well. Right? And you will see eventually there will be one for different types of cancer as well. Right? That's being developed. So then we bagged our gowns and things like that, and students would come in here. And so at the very far end, we have a helium cadmium laser, 42 milliwatts. That's used for making, you could do holograms with that, but that was made used for making Bragg DFB lasers, so based on the Bragg grading system, where you're essentially beating light against itself, and you're getting a pattern that's sub-micron. And that could be used, for example, in optical communications, but in strain gauges for bridges, optical strain gauge for a bridge, as opposed to a mechanical strain gauge that civil engineers might use. So the students would come in here, they would be trained to use this equipment. On the other side, we have equipment that supports the research, your samples that you're making. So at the very far end, ultra-high vacuum system, UHV electron beam gun. And a gun is just a tiny little filament made out of tungsten. If you put 50 to 100 amps across it, electrons come off thermionically, and you have a magnetic field that directs them into a pot of gold or a pot of other material that you have in there. And so what we have is anything in the past that was related to 3-5 semiconductors. So we have nickel, germanium, gold, which is a typical contact scheme for 3-5 semiconductors for making ohmic contacts. Titanium, platinum, gold, which is a p-type contact. And then there's one more metal because it's a 6-hearth metallization system, chromium. Chromium is often used as a surfactant, so if you wanted to put down a noble metal like platinum on glass or whatever, you would have to put chromium or titanium down first to get it to stick, otherwise it wouldn't pass what's called the Scotch tape peel-off test, where you put Scotch tape down and if it peels off, it's just not sticking properly. Right? And so chromium is also used by a research group here that's working on lithium niobate semiconductor material, which is a nonlinear optical crystal, and they're doing what's called polling of the lithium niobate, and their research is mainly for either for laser research using lithium niobate, or they do long distance satellite communications as well based on lithium niobate type lasers. Right. Are there any questions? Okay, so what we're going to do is go and peek in the back end of the clean room. I'll allow people, since I'm the gatekeeper, I will allow people to come in not being gowned up, and we'll clean up afterwards, or after these tours I will probably vacuum and clean up this place a little bit better than I would have otherwise. Okay, so let's go down the hall and take my water bottle with me if that's okay. So did you say you were both at Waterloo? Or-
No. The people who didn't show up were from
Oh,
Waterloo.
what, and yourselves?
I'm McMaster, Western.
Okay.
CMU.
And what are you studying?
Computer science.
Electrical
so-
engineering.
Okay.
Engineering physics.
Oh, you are in
Yeah.
engineering. Okay, so I haven't seen you here.
Yeah,
Yeah.
no, I haven't done any lab work yet. I'm just.
Oh,
yeah.
okay. Because usually I see the students because there's an undergrad lab here as well. Okay. Let's just look in the back end. So we're just coming in the back end of the clean room where we have slightly fancier equipment and stuff. Peek in here. So people working on silicon photonics have to do waveguides, making of waveguides, doping of waveguides with rare earth materials to make them, to change the index of refraction. So we have a sputtering system, for J. Lester sputtering system. So if you want to take a look, you can actually come past me and look inside.
Thank you.
And so these are the different sputter targets. So for depositing silicon dioxide, silicon nitride, and silicon oxynitride, there are people interested in hafnium oxide now and things like that. And then doping of those. So changing the optical properties by doping with rare earths, such as tellurium, some of the rare, there's not a rare earth, but some of the rare earths as well. Europium, erbium, and tellurium for changing the optical properties. Then deep reactive ion etch system for making these reactive ion, bridge waveguide lasers, and a direct writer where you're directly writing with a UV laser on your sample, and it's a UV sensitive photoresist. Okay? So then we'll go down the hall to the optical characterization lab and other forms of characterization as well. So we're also in charge of like maintaining all this stuff as well, right? And there are two of us. Hello.
Thank you.
So a lot of people are working on material science aspects, trying to develop materials for particular applications, typically engineering applications or bio applications, but you have to be able to characterize these. And there's different ways of characterizing, whether it's electrical characterization or optical methods. And so if you're growing thin films, one way of characterizing your thin film is ellipsometry. And we have a variable angle spectroscopic ellipsometer, a vase, so that provides a light source from the visible to the UV. And I can talk about what that equipment is that you're, and it's all ancient equipment too, but a vase is to measure the index of refraction of the material, and then you can get the thickness, and from the index of refraction, you can get the composition too of the material. But you have to give it a starting point, right? You have to, you know that you're on silicon, or you better know what your substrate is, and you have to sort of know, don't take pictures of junk. We're in the process. What's happened is we've had to, I've lost a lab next door to a Canada Excellence Research Chair, and so I've had to move a lot of stuff in here, and I don't know where to get rid of stuff and whatnot. But anyway, a vase will tell you then how thick your film is that you've grown, index of refraction. Is it SiO2? Is it suboxide? Is it, is there more silicon in there, or whatever? Is there a contaminant in there? So it's not giving you the index that you expect. So one optical method, another optical method is we have an FTIR. It's covered there to keep dust out, but it's a Fourier transform infrared spectrometer. Again, that can be used for anything from measuring, for example, nearest neighbors. If you're doping with the rare earths and whatnot, to know the location of them. I'm just listening to what that noise is, but I guess the air conditioning came on. It was quite hot on Friday, yesterday. And they've actually put the air conditioning on as opposed to heating. It was too hot and they were overheating this lab. But the FTIR can also be used to measure optical properties of materials and even the nanowires, because you have a microscope that can zoom in on individual nanowires. And then you could see if, do they absorb light? Do they transmit light? What the reflectance is and things like that. And then a quick and dirty sputtering piece of equipment, 2 sputter targets, DC and radio frequency. 2-inch diameter targets, and so again you have an argon plasma and you're essentially removing or splitting material by a sputtering process, typically for putting down either ohmic contacts, or a lot of people put down gold on polystyrene, for example, which is, for a semiconductor people, that seems unusual, but then they heat that up and they shrink it and you get more surface area, and they use that as biosensors. So I'll show you then when we go to the other lab a much more fancier and more modern piece of equipment that does the same but on a larger basis, and where you can run rolls of polystyrene through. And so it's a roll-to-roll sputtering system. Okay, so what we're going to do is just go down the hall and look at the showcase, especially if, I don't think anyone's probably shown you that, have they? It's in the hallway in engineering physics. Okay, so we'll just see where students ended up and some of the projects the students have worked on in the past in 4th year for the capstone project. Okay. And I didn't talk about this, but this is a laser for measuring band gaps in materials, so it's photoluminescence, belonging to a very particular research group. And so then you can measure the Fermi level in materials and the band gap. Okay, so let's go back to the showcase, and I'll talk a little bit about the students who came through engineering physics, just to give you a bit of background to where you might end up. Okay, so these are some of the graduates of engineering physics, either the bachelor's or a master's, so you might recognize, if you're from Waterloo anyway, Donna Strickland, who got the Nobel Prize, right, a couple of years ago. Does it say when she got the Nobel Prize? But she was an undergrad here. Yeah, 2018, she got her Nobel Prize. So she was an undergrad here and a summer student in one of the optics research labs in Work Science Building. And this Nobel Prize is based on her PhD work in Syracuse, and that she shared with her supervisor and a French person, if I'm not mistaken. But we have other people who have worked here as well. Tahara is at Apple now. Tahara married a person who was in engineering physics who also had a PhD at Apple. Despite the fact that they're together and married, they are not allowed to talk about any of their work, any aspects of their work. They sign them. Yep, non-disclosure agreements, and they would probably love to bounce ideas off of each other, but they can't, right? Because the research groups are kept very, very separate, so they don't know what the other person is doing. Right? I suppose if they were in the same research group, it would be fine, but they're not.
Do you know in what area she's working?
Yeah, well, it has all to do with your phones and stuff like that. So they're all coatings and things like that. And both of them would be, because they came through here actually working in our clean room facility. And actually, they can't really talk about what areas. It has to do with the displays in their phones. Or
I'm about to going home. Oh, how was work today? Can't tell you.
Yeah.
They can say it was hard or whatever, but they can't bounce ideas off of each other.
Wow.
Right? They would like to, I think, because they're both very smart.
Is
as
it
well.
for fear of competitors, like
Or somebody
answering-
or somebody finding out, sure. Or someone within our spies or whatever, sure. Yeah, people are very secretive about stuff like that. So, okay, those are examples of people who ended up at Apple, but we have other students who are at Apple as well. Some have come back, some work for L3 Harris, for example. L3 was L3 West Cam as engineers, but one of the guys at Apple came back and wanted to live in Canada and be in Canada to be closer to family, and so he gave up a very good job at Apple, but there was a lot of traveling as well. But those people who are at Apple quite like it there. But unfortunately, a lot of people have to go to places like that because with the skills that they have, except for the Ottawa area, and there are smaller niche companies or whatever, then you have to adapt and try and find jobs as well. And a lot of people ended up doing AI. I mean, yes, it says he's a sales engineer, but he now has his own AI company. This guy has his own AI company as well. A number of women and other people came through, these two women in particular came through medical physics as well. So they would, they would have bachelor's or master's degrees, and then they would go on to become either medical oncologists or radiation therapists and physicists, right, with the background. They would train at the hospitals in Toronto for that. So if we go down maybe to the showcase here, I can just show you some of the stuff that the students in fourth year in particular have made or used. We talked about the solar cells with the etched pyramids in it. That's your renewable energy, the 4002 undergraduate lab. They've also made infrared detectors. They've also made the ion-sensitive field effect transistors as well, the ISFETs. What else do we have? Another ultra-thin solar cell. And then there's the capstone projects. The capstone projects are the project that they do in fourth year, right? And so, I mean, when they first started out with the capstone projects, the professor would choose what the project was. And often, back then, this is many years ago, you'd have a vehicle, some sort of autonomous vehicle, and you'd have to race it against your classmate's vehicle to get down to the end of the hall. So how do you do that? I mean, what they used to do back then is sounds funny, but put black electrical tape on the floor, and you'd have to have something that followed the black electrical tape. But it got more sophisticated then over the years. And then you'd have to have your vehicle come down the hall and park into a garage, or start over here and go around the corner. But this hall is pretty flat surface, and if you practice in another building, it might be wavy. And so that led to complications. But you can make it more complicated by saying, okay, now you have to go outside. You have to go outside, maybe it's snowing, maybe it's raining, the sidewalk's full of cracks and bumps and stuff like that. How do you build your vehicle? And then they've changed the projects over the years. And for example, this one was a professor in engineering physics who had them do or find liquid in a cup. There were 6 cups on the table. Only one of them had liquid. The liquid was either water, milk, orange juice, Coca-Cola, different colors, different whatever. And so you had to find the cup that had the liquid, bring it back to a testing station, and decide what the liquid was. And not everyone got the same liquid. Maybe somebody got the milk, maybe someone else got the milk, someone got the Coca-Cola. So how would you test that? You're looking for pH, maybe for the acidity of it. Maybe you're looking at the absorption or reflection of the material, electrical properties of the material and stuff. So you had to build a vehicle like that. That was that one professor, but then there was another professor who was a nuclear professor, so instead of having cups there, he had a sandbox full of ping pongs, but one of the ping pong balls was radioactive. So now you have to dig through, make some sort of digger, pick out the ping pong balls, but pick out the one then that was radioactive, measure it, and find out how radioactive it was, obviously, yes.
So the autonomous car race thing you were mentioning, how did it get more sophisticated over the years?
Well, as I said, you'd park, for example. You wouldn't necessarily put black tape on. You would
Oh.
find another way of, you'd have some sort of beacon or whatever at that end, and you'd have to find it, optical methods,
Oh.
rather than following
It's
a
like you have
piece
to
of
like
black.
change your approach over the years.
Of
to
course.
make sure it's the same thing.
Of course, yeah, because, I mean, not everyone's going to put down black tape into that,
Yeah.
but, you know. And I remember one year, and then first of all, you're also working as a team, so you have, they're marking on how you work as a team together. You're competing time-wise, race-wise, with your other, like which car gets down there faster. Usually it was a car. They looked like cars. Right? There was a budget thing. You'd have to keep track of the budget and keep it cost-effective, right? So you got points for all of that. And actually, back then it wasn't easy to do. Now it's much easier with the internet. You can look up a lot of things. And now it's completely changed. You don't have a project like this. You pitch like the Dragon Standard project. So you come up with some idea, whatever that idea is, potentially to help society, whether it's to help, whatever, with something with drug sorting or helping greenhouses up north or whatever, or indigenous communities. I mean, people have some interesting ideas that haven't maybe been implemented. Some have, but maybe you're improving on them or whatever. Right? Okay. Are there any questions about this? Okay, so what we're going to do now is go over to the Tandem Accelerator building, and I'll just show you some of the equipment there. And that'll be it. We don't have much time. I mean, it's about 15 minutes, right? It's the most. Are there any questions? Nope.
Wait, we are going to come back and grab our stuff like I did.
Yeah, let's do that first. Yeah, I forgot about that. Good you reminded me. We'll just stay inside the building for a bit, walk through, and we're heading over to the Tandem Accelerator building. Okay, so we're just going to go through some hoarding. This used to be the McMaster Materials and Manufacturing Research Institute. They have moved to the industrial park on Longwood. And all of the space, which used to be a beautiful machine shop and research and development area for cutting tools and turbine blades and things like that, is now in the industrial park, about 5 minutes by car, just east of here. And this is all going to become makerspace, essentially, for first-year engineering students for their first-year projects, which are compulsory. So we're just walking through the old engineering building, through the main lobby, and to the Tandem Accelerator building.
Thank you.
You're welcome. You can see there are a few people studying here. Sometimes people play piano. They actually play piano quite well. They are classically trained musicians. And then you can see we're showcasing some of the students who are in the master's and PhD programs. Their posters are up on the wall, telling the story of the research. Many of those students I would see in our clean room facility. They'd use some of our facilities to characterize their samples or produce their samples in the first place. So I don't know if you know, did you know there was a reactor on campus?
I've heard.
Yeah, the nuclear.
Yeah.
Yeah, so it's a, I think it's a 4 megawatt reactor. It's a research reactor. It does not produce heat or energy or whatever, but is used for producing isotopes. Here, for example, the one student that uses our facilities quite a bit in ChemEng, right? Renewable energy to convert carbon dioxide into fuel cells and chemicals. So again, not Eng Phys background, but he uses our facilities. So he does a lot of sputtering as well. Let me just sign us in. Okay, come on in. So welcome to the molecular beam epitaxy lab. You're taking all these pictures of stuff. We're in the process of trying to clean up this lab and get rid of junk. As you can see, there's a lot of junk. So my colleague and I, there's only 2 of us. We've inherited this lab from other people that used to work here. So one of the newer pieces of equipment is a femtosecond laser, a Femtica from Lithuania, used for writing down at the submicron level patterns in photosensitive materials, similar to, let's say, a direct writer or lithography, but at a much smaller scale. Behind me here is a ion implanter. So this is the machine that I had a lot of experience with, running in different labs as well. We have different ion implanters. Western has a beautiful ion implantation facility. And so an ion implanter was typically used in the past, and I haven't used it much in the last few years, but we're trying to resurrect this machine, but for doping semiconductors. So if we were working with silicon, we would implant boron, using boron trichloride as the P-type dopant, the boron, or phosphorus as the N-type dopant. And so when the undergrad labs wanted ion implantation to make their PN junctions, I would do the samples for them. Now I think they use spin-on dopants. People are interested in the rare earths. The rare earths are there to, again, dope materials to get light emission at different wavelengths, and different colors and stuff like that, to try and replace the solid state light, for example. Or you're doping your waveguides with tellurium or other rare earths as well. And then there's medical physics people applications. So there's a company that I worked with called Kinetrics. They used to be Ontario Hydro Research Labs, but they're on Kipling Avenue in Toronto. They were interested in ytterbium. It's not proprietary as far as I know. They've commercialized this as well. But they wanted one particular isotope of ytterbium, ytterbium-176, that they wanted me to try and separate using the ion implanter. And I'll have to say I couldn't because the optics did not allow me to do that. It would have to be changed to make it more feasible to distinguish all the different isotopes. And if they had 176 as the isotope, I would get a mix of all the isotopes. I couldn't separate them very well. They would take the 176, they take it up to Bruce Power. They are commercially doing this, and they're making lutetium-177, which is used in prostate cancer treatment and treatment of certain cancers of the endocrine system as well. And so there is some interest in revamping or trying to get an accelerator to study some of the possibilities of using other medical isotopes, in particular for, you can use it for diagnostics, but in particular for treatment of certain types of cancer. So sometimes I explain how an ion implanter works, but it's essentially an ion accelerator. You have an ion source, you have a filament, tungsten filament. You put a couple hundred amps across the tungsten filament. Electrons come off thermionically. There's a magnetic field that confines them in the air, confines the electrons in the area of the filament. Usually I run argon as a carrier gas, so I strip off electrons, ionize argon. I always work with argon, and it's very typical. It's an inert gas, and we know that argon is at mass 40. And then you could use either, as I said, for boron trichloride, or silicon tetrachloride, or phosphorus would be a red phosphorus powder that would be loaded in the back of the oven, and you would heat it up. And so I would always check where argon is down at my target, because a charged particle, positive particle moving in an electric field, will get bent. And so you have the ion source sitting here. Positive ions get pulled out by a negative extraction electrode, go through a magnetic field, they get focused, they get scanned, and then you implant on your target area. And yeah, are there any questions about this? So essentially you're changing the material properties, the electronic properties, the optical properties of the materials. You're making materials that luminesce. Sometimes we do silicon into silicon, which sounds funny, but you're making silicon nanocrystals and they luminesce. You do germanium into germanium, silicon, high dose silicon into germanium as well to make the nanoparticles for different materials to coalesce and luminesce. Next three pieces of equipment are chemical vapor deposition systems. Again, that's for depositing silicon dioxide, silicon nitride, silicon oxynitride, silicon carbide. Again, for coatings, they could be hard coatings. You could make coatings on windows so that when you spray water, it just self-cleans. You could use those in certain types of devices as well, passivating devices, your anti-reflective coatings on your lasers and things like that. You could do amorphous silicon. We have one PhD student, a lady who's finishing up. She should be defending in December. She's trying to make nice solar cells. And when I say nice, I mean pretty colored solar cells. She's working with GM. I think regular solar cells, every car would look the same color, a brownish, dark color. That's not appealing for buyers to buy electric vehicles. So she's working on different multi-layers and studying your solar efficiency, but also measuring the index of refraction and seeing what colors make cars that are desirable for people who want to buy electric vehicles. I'm going to call it. Excuse me. I'm going to sneeze as well. This is all on. Is this all being tape recorded? Am I coughing? Am I sneezing? Okay, Hall effect measurement. When you do ion implantation, you're doping your sample. You're changing the electrical conductivity, the mobility of the sample. You're putting in more carriers. So you do what's called Hall effect, 4-point probe measurement. Magnetic field comes in perpendicular to the sample, and then you can get information about, did you dope the sample? Usually you have to do anneal process, and our annealers are upstairs, because you're putting in these ions essentially randomly into your material. You usually angle it so it goes in, not down the straight channels of the silicon or whatever. And excuse me, when you anneal it, your dopants sit then on the lattice sites and would contribute to the conductivity, whether it's p-type or n-type or whatever. Okay. Then at the very end, we have the famous molecular beam epitaxy system where the samples were grown. Unfortunately, our grower has taken a job in the United States in Phoenix, Arizona, and he's now a silicon germanium grower for industry. Can't really talk about his projects and stuff like that. Again, it will be for places like Apple, and I think they work with Infineon as well. This is Angstrom Engineering. So Angstrom Engineering is a Waterloo-based company. I worked with them years ago when the founder of the company was a research engineering designer for UHV Instruments, which is a Burlington company. But they're doing roll-to-roll deposition of gold. So you can see that's some of their scrap gold. And we save that because gold is very expensive as well, so we recycle that in the end. But there are people working on nanobots, nanorobots. So they're trying to look at hemoglobin and problems with people's blood vessels and stuff. So they have these little magnetic robots that will be put into your blood system, and you can direct them with magnets to your heart or wherever you have to go. Okay, so students are trained to use this equipment, to run the equipment. I did talk about atomic layer deposition system, but we are getting that as well to put down some of the oxides, materials, aluminum oxide as well for making devices. And then the MBE system, 3.5, molecular beam epitaxy. So these are the hazardous materials in this lab. I mean, you took a picture of a gas. I don't know if you got that. That was a phosphine bottle that was on the floor. ASH3 and PH3 are the toxic gases, but you can see there's an issue here. Right? We don't have an MBE grower, but upstairs we have a MOCVD based on the same gases as well. So we are trying to clean up the labs. We're trying to take inventory, figure out what we have. A pump just came back that was repaired yesterday. So that was shipped actually to the United States to be repaired. And we're just going to go through all the supplies and stock that we have. I tend to be a hoarder to a certain extent because you never know when you need something. But we need to make room for new equipment as well. Let's go upstairs, and we're almost finished then.
Thank you.
And just keep in mind there are 2 of us working on all this equipment.
Yeah, it must be a lot.
It is. So I talked about MBE downstairs, molecular beam epitaxy, where you're using the template of the substrate, which is crystalline, to grow your layers of gallium arsenide and indium phosphide and combinations thereof. But you have MOCVD system, metal organic chemical vapor deposition system, same gases, arsine, phosphine. There would be silane for doping, that's your silicon. And so students would grow things like nanowires here, and the nanowires could be wires that could be used as sensors, they could be used as detectors, photodetectors. You could make your quantum dots as well, that can be used. And then some of these nanowires can be used to mimic electrodes, like the neurons in the brain and things like that.
How old is that computer?
Old. So these, and you can't replace it because these pieces of equipment are rapid thermal annealers. So the program will be on a DOS-based system. So that's one of our problems with a lot of stuff that we have. It's very hard to upgrade. If you upgrade in the software, it doesn't talk to the equipment. So these are like, they remind me as a kid, I had an easy bake oven, which had lamps and you could cook cookie dough and stuff like that in there. Here you are annealing with lights. So they would be tungsten halogen, high-powered lights, in the kilowatt range. And you would quickly ramp up the temperature in a few seconds to about 1,000 degrees C. You might work at 1,000, 1,200, maybe a little bit lower. You would have to work lower with things like gallium arsenide and indium phosphide because the arsenic and the phosphorus would come off. And that's for annealing your samples after you've implanted them, changing the electrical properties of the materials. Okay. We are thinking of upgrading this whole place to maybe make it a clean room facility, so all of this stuff would have to go. They have to either be put somewhere else, or you get more modern anneal furnaces and stuff like that, right? Like they use in industry. Okay. Dicing saw for cleaving samples, cutting samples. So that's a relatively new piece of equipment there. This is the old one, which I haven't got rid of yet, but. Okay, and that's it for our tour. If there are no questions, you can talk outside. Clarissa should be coming by the back door. Usually that's what she does. Okay, let me just see if usually she knocks on the back door. We'll just wait here. Are there any questions? So what are you studying in computer science?
I'm doing like all software. Here, I'll just.
Sorry.
Oh, and I'll turn this on. It should just be another. Sorry, my keypad is broken, so you have to use this mouse. Here we go. Okay. Am I unmuted, Emily? Okay, awesome. So for everyone online, the CDT tours are quite a bit behind schedule, so we're going to get started. We're going to do the presentations in a little bit of a different order than what's on the schedule. So first, we're going to start with James Brown from QBraid, and then Sasha is going to give her presentation, and then QAP. So first, if you'd like to introduce yourself, James.
Okay. Hello. Thank you to the organizers for inviting me. I'm James Brown, and I'm a research scientist at QBraid company, the quantum cloud. So there's three main parts of QBraid. There's QBraid is a quantum computing orchestrator. So we host 20 plus quantum computers, CPUs and GPUs in the cloud that people can access easily through our platform. We are a software integrator. We have our QBraid runtime, which allows you to move easily between 15 different types of quantum computing software across different modalities, meaning like ion trap or superconducting or analog. And we're also a research innovator, and that's the part that I'm mainly a part of. And our researchers have been cited 4,000 plus times and have deep experience in returning business value. So we'd like to say we're the most connected quantum computing startup in the world. We have access to 15 plus QPUs, 15 plus software development kits or quantum computing software development kits. And we have 24,000 users on our platform, which for a niche field like quantum computing is actually quite large. And I think the largest of any similar company. So our one of our main parts is QBraid Lab, and that's something that you can access from your computer, and I'll have a demo later in the talk about this. And this is where you can code in quantum software and also deploy or submit circuits to quantum devices. Another part is QBraid Hacks. This is where you can run hackathons on our platform, just so everyone can have the same environments that they're using. And then QBook, which I'll also show later, is where you can learn about quantum computing in an interactive manner through videos and running code live. Closer to the hardware, which is, I believe, what this hackathon is more about. We have these three products here. So there's QBraid SDK. This transpiles your circuits from any language to a different language and then submits it for you to the device. And if all goes well, I will show that later as well. I'll submit to a real quantum computer. QBraid runtime is something that sits even closer to the hardware. This interfaces with people's different companies' quantum devices. And theoretically, if you had a quantum computer of your own, you could deploy it there and then give people access to your device through the cloud. And we have we give access to more quantum computers every week. And then QBraid pilots, which is the part I'm mostly involved in, and that's to provide proof of concept work for different companies who are interested in exploring quantum computing. So this is more on QBook here. So this is something, this is a demo you would see if this was, this originally would have been a movie showing this sine wave moving, but I can show that later when I demo the platform. But this shows that you can have an interactive portion while you're learning about quantum computing. So the hackathon part, more in depth here. We provide the experience, so the platform that you can use for your hackathons, support for when you're running your hackathons, and this we can also provide mentorship and device in the future. Lab, I will provide a demo later, but this is what it looks like. You can also have it in a VS Code mode if you're more interested in developing software that way. This is the Jupyter Lab notebook mode. And then QBraid OS, this is the part that gets closer to the hardware. So we've got we have some debates about whether this pyramid should be inverted, but you have the SDK, which is what software programmers would interface with. And then runtime would be the interface between the programmer and the hardware. And then gateway is the interface to the runtime there. And it's the on-premise deployment to orchestrate jobs that are submitted to our platform. So this is one of the key selling points of our platform. This is the different way, this is the transpilers. So if there's an arrow connecting one to the other, then you can say code in Penny Lane and submit to the IonQ device there through our platform, or to Broquette, which gives you access to a bunch of different devices. And also, if you want to do Clifford simulations, there's STIM, but you can go back and forth between many different languages. So the main point of our platform is that we did not want to tie people to a specific quantum computing programming language. We wanted to make it easy for people to code in any fashion they like and then submit to quantum computers easily. So this is QBraid runtime, and this is the on-premise deployment. So this takes in, this will tell you which devices are online and what devices people can submit to. And also this provides an interface between GPUs and CPUs and your QPUs if you would like to submit hybrid jobs and you need that connection. And once again, it's with its connection to SDK, you can submit in any programming language you desire. Another main thing we like to focus on is community building, and especially in the quantum software ecosystem. So here we have this quantum intermediate representation. So this is an open source project that you're welcome to contribute and look into that provides, if you know, like LLVMs or lower level compiling, that's the goal of this project, where you can develop hybrid applications that will run efficiently, and this should run closer to the hardware. As far as, so this is, the goal here is you've got all these programming languages on the outside, and we have this, we also have an OpenQASM, PyQASM version that's a little more feature rich than the Qiskit or IBM's OpenQASM. And then this can be submitted to a quantum intermediate representation that can run on the hardware. QBraid Algorithms is a project we're working on right now that we develop different algorithms that you should be able to take and plug into your own development of algorithms. So right now, quantum reservoir computing is something we're very much looking into, and we've had some recent research on that, which I can talk about after, but is not going to be discussed here. But we've got different algorithms there too, quantum Fourier transform and some other primitives that you can use with your research. We also upskill people with we like to say that you can get access to all the quantum computers with just 5 clicks, which I'll show you later. And we also have many different collaborations with universities to upskill their people there. And at the top right there that's from the Open Quantum Institute, and that's a project affiliated with CERN. And there we're working actually with a McMaster professor on accelerating antimicrobial discovery with quantum computers. And that's a current project that I'm working on. These are all the hackathons that we've supported, and as you can see, it's all over the world. This isn't even the most up-to-date list. We had some in Uruguay and Greece and Egypt and Thailand this year, and that's affiliated with that Open Quantum Institute. Yes, we're very much have a presence. Training is a part that I'm heavily involved in. So these are the different universities that we've provided some workforce development training to. And this includes Dartmouth, that's where I did a postdoc, and MIT, many different universities. QBraid courses, this is all done through our QBook platform, but there's many different university professors who help teach their courses with the easy-to-use interface we provide. And we've had some affiliations with the White House as well. This is some other workforce development we've done. So a boot camp for 60+ students, and this provides an in-person hackathon, access to QBraid Lab, and prizes in the form of internships. And now finally, I think this is the last part of the talk before I move into the demo. But research, which is the main part I'm working on, and you're welcome to talk with me about it after. But we were on this Quantum for Bio project where we tried to use quantum computers to solve a biologically relevant problem. So here you can't simulate a full protein on a quantum computer at this point. So our idea was that you use something called fragment molecular orbital, and you take these very large molecular fragments and break them into smaller ones. And some of those are going to be classically tractable, which means you could simulate on the classical computer. For those fragments that you still can't calculate classically, we had 2 different methods we were examining. The bootstrap embedding and localized active space. And these just make it even smaller because current quantum computers are very noisy at this point. And then there's some error correction work that we just put out a paper on that I'm more than happy to talk about as well. This is another project we'd worked on, and this is with Airbus. working on flight trajectory optimization. And this won an award at a IEEE quantum computing conference a couple years ago. Yes, so we've done a few multi-year projects on quantum computing, and this is, yeah, if you're interested in learning more, yeah, please come and talk to me. So this is the contact information. I will pass that. I'll give you a chance to take a picture of that if you'd like, and then I'm going to move on to the demo.
Okay, you got it.
All right. All right, so this is, maybe I'll start at the main, what you would launch. So this is our main account.cubebraid.com, which you're all welcome to go to and sign up now if you would like. This is the different places. So devices you can click on and see all the ones that are available. Rigetti here, which is I think we're going to run a circuit in a little bit. Quantum jobs, these are previous tasks that I've run. So I've run on Rigetti before, and you can see that I ran a 100-shot job of something, which I think I'm going to do again here. But here was one on QEra. This is an analog device that you can run simulations on. It's a different type of quantum computing at this point, although they are moving on to gate-based with their device. Hackathons, these are just examples of previous ones we've affiliated with, so you can look into those. Here is courses. So I would suggest looking at the Cubes beginner course if you're a beginner. Not all of this is available if you're on a free plan, but for example, here's some videos that are embedded, and then you can take a quiz. And more interestingly, we're going to move to qubits, gates, and measurements. Let's see. So this has code blocks here. So you can run that. Measured outcome is 1. This is a Hadamard gate, so it should be randomly going between 0 and 1. There. If you just want it to be 1, you can interact with this as well. And then it'll be 1 every time. So you can learn, change your code as you go through the course. Back to here, we also have Composer that you can look at. This has other examples that you can even learn about magic state distillation. But it's just an interactive way of learning about what happens when you run a quantum computer, and these are the block spheres for the different qubits. So for example, I could do a GHZ state. So I'll put Hadamard on the first control and a not. And then you can see that it's a 50-50 probability of 0, 0, or 1, 1. Now back to running on a quantum computer. So how I got this here was just a second. So if you go So QBraid Lab demo. And then there's a launch on QBraid button. And you might see this in other places as well. We have a collaboration with Xanadu. So some of their stuff you can open on, there should be a launch on QBraid button there as well. So this is in the folder QBraid Lab and Quantum Jobs. So this is a notebook, and you can run the code cells here. And once again, I'm going to do I coded this in Amazon Brocket language. So here's a Hadamard and the same circuit I did in the composer earlier. Here, this is a state vector simulator, so I could run that, and that's the device I'll choose and run it. So this is going to submit a job to just a regular CPU at Amazon. And you can see that it should approximately be 50-50 between 0, 0, and 1, 1. Once that completes, there we go. So it's not quite perfect because of the randomness of sampling, but that did now show up in the jobs tab here. And it was, there's a new, yeah. So this is the results here. All right, now let's see if we can run on that's the list of jobs that I did before. Here's the devices. So it says that Rigetti's Anka 3 is now online. So if you go here and you copy this ID, what's that? And here, I'll try and do this one-handed. All right, so let's try and submit it to an actual quantum computer and see what happens. All right, it doesn't appear to be working right now, but yeah, in the past I have submitted to Rigetti here. And you can see that, oops. All right. So another feature we have on this is all right, environments, which so here this was the environment I'm using is for IEEE Quantum Week tutorial that I did. And this is this has a bunch of things that were necessary for running the example notebooks that we used in order to teach people about quantum computing. But yes, and I think yeah, I think that is all I have for today. So if you have any questions, I'd be happy to take them. Thank you.
So it seems like QBraid is working on a lot of very interesting projects, but there's many of them. you feel like that is that enriching environments, or is there ever like competition for sort of resources, so like your like focus divided between many bits of.
Would you also be able to repeat the question, please, for the online participants?
Okay, so the question was essentially that there's many things that happen at QBraid. And is this overwhelming, I guess, or is there competition for my time, or is it an enriching environment? I would say we have so there's things that do need to get done, but I think a lot of what happens is we have a lot of freedom at a smaller startup to kind of do what we want, and this is kind of the outcome of that. We have the ability to tackle many projects, and yeah, most of the time you have a lot of freedom with what you want to do. So that's I'd say enriching more than constraining. Yeah.
I saw on your one slide add a scheduler. It looked like a web where you could say go on HardHaQ's device to schedule a job, something else. I feel like that gives you good insight as to which kinds of quantum computers would be better for different tasks. So yes, can you speak on that?
So the question was about scheduling on devices. So here, oops.
Sorry, use the middle.
And how that would help you decide what you could run on. So so they're very expensive at this point to run on a quantum computer, and also the speed at which you run it. So ion trap devices are quite slow and quite expensive per shot. So I would say that I would not use it unless you need higher accuracy results. But if you do need higher accuracy, I would run it. It would just be more expensive. So if you look at the per shot and per task, so this is so 30 credits is about 30 cents per task, and then that would be 3 cents per shot. So that 100-shot job that I would have done would have been $3.30 on IonQ. Whereas if you go to, say, Rigetti, which is much faster, but not as good of device, you can see that you have the same 30 cents, but then per shot, it's only 0.09 credits. So it would have cost 39 cents instead of $8.30. And you'd get your result much faster, depending on the number of shots you're using. So
and what exactly makes one of the devices more expensive to run versus the other? Like, is it the physical energy required to do a shot on the device?
I think mostly it's the time that you need to run that. So yeah, it's superconducting is about an order of magnitude, maybe a couple orders of magnitude faster than ion trap devices or neutral atom. I think neutral atom is about, that's Quera here, Quera. Yeah, theirs is, so that would have been $1.30 for Quera, but yeah. All right, seeing no further questions, I've used 29 minutes, so.
Can we get another class?
So next, please welcome Sasha Joshi from CMC. If you could give yourself a brief introduction.
Hi, everyone. I am Sasha. I work at CMC Microsystems in the capacity of a staff scientist. My work is majorly on the software side of the things, very different from the topic of the hardware hackathon here. However, I'm just going to introduce what my company does for those of you who are hearing CMC Microsystems for the first time. We are a nonprofit organization with 40 plus years of existence, I would say. And we have people who are expert in using or accessing tools for fabrication, essential design and fabrication services again, and skilled engineers and technologists that have the portfolio in addressing the deep tech requirements of Canada. Currently, we are leading the fabric funding by ISET. This is a 5-year funding program, which mandates or the aim of this program is to galvanize and improve the deep tech situation in Canada, particularly in photonics, compound semiconductors, MEMS, and for this topic, for the hardware hackathon here, quantum technologies as well. So what actually is Fabric about? So Fabric essentially comes off as challenges. So we present rounds of challenges that you can participate in, and we would provide you funding through ISED to develop the product that you give submission of. So under challenge funding, the process and product will take your ideas and we'll see if you can actually commercialize those ideas. And the money you require to commercialize those things, we would provide you funding for that. We also have design and fabrication tools to help you design and lead that project to a commercialized level, provide you low-cost access to all of these tools and fabrication facilities, as well as train a pipeline of highly qualified personnel. So if there are people out there who haven't used these deep technologies or including quantum technologies, but they're interested in finding out if quantum technology can work for their business development or for their business, or if they have an end sector goal or application for the current business, we can also train them on these deep technologies and help them build maybe a minimum viable product that can be further commercialized. And again, we have an extensive domestic network of academics, universities, commercialized labs, and government sectors as well, pan-Canada. So Fabric is this 5-year window where we, again, release these challenges to strengthen pan-Canadian ecosystem in deep tech. Most recently, we've had 2 Fabric challenges and 2 rounds of these challenges. And under these 2 rounds, we had 2 different streams where academics or small to medium scale enterprises or even nonprofit organizations could apply for funding. And these 2 different streams were fabrication process development, which focused on building new or improving existing process capability with photonics, quantum technologies, MEMS, or compound semiconductors. So if you have an idea that can be commercialized under these topics, you can apply under the fabrication process development in further rounds. And the second area was product development of IoT devices, which particularly supported development and commercialization of advanced sensors and other semiconductor and IoT related products. So the challenge covers up to 40% of your R&D project costs. And if you're coming from an academic institution or smaller, medium-sized or medium-scale enterprises in Canada, particularly, you can apply for funding under Fabric. In the first round, which was released, the challenge call was released last year. We had particularly 4 companies qualify for quantum technologies or under the umbrella of quantum technologies. For fabrication process challenges in the first area, we had Epinix, Anion, and Quantum Recon. Whereas for product development challenges, we had Cubic, and these companies were qualified for the funding rounds. While the second round of Fabric just ended somewhere on November 10th or 12th, I'm guessing. We are yet to hear who the winners would be. Yeah, further rounds would still come, but we just completed our second round. Now, what is Fabric, particularly for quantum technologies? Now, under Fabric, we are taking this initiative of bringing quantum technologies to the market by doing three utmost important things: developing, adopting, and commercializing the technology. By developing, we mean we are bringing in all the academics and small to medium scale enterprises together or individual to help them learn about what quantum technologies can do for their business, which end sector applications they can work on. Or if you have any idea, then you can come up to us and get our help in developing those ideas. By adoption, we mean developing either a minimum viable product or sitting with you and building a roadmap so that you know where your product can galvanize or combine with the quantum technologies available outside. And finally, we also bring a roadmap or set up a roadmap with you if that minimum viable product can be further commercialized on a large scale level. Along with that, we are also working in enabling Canadian companies and researchers, particularly the ones that do not come from a background in quantum technologies, to adopt these quantum computing solutions. We sit with them, if they want to know where quantum computing can take their company further, we sit with them and we tell them they have these particular options and this is how they can bring their product into the quantum sector as well. And again, develop quantum-based products and devices, which includes both fabrication, help them with fabrication, or help them with software solutions. In more detail, under the training part, we also have upskilling training for high qualified personnel. Most of the students here might have heard about CMC through the semiconductor workshops, which is a part of this training method or this training umbrella where we organize these workshops every year annually across Canada. And you can come and learn how these technologies work, while also you can come and fabricate a very small piece of chip or very small piece of the project that you're building for learning purposes. Second is quantum application development, which I've been telling you about and which I'll also be discussing in one or two slides further, is how you can get access to the different technology out there, different cloud-based quantum products and infrastructure, and submit your projects onto those cloud-based infrastructures, and then get results out of them. And finally, we have device design and prototyping as well. We are in collaboration with various government-led and commercialized labs out there that we can provide a cheaper access or subsidized access to fabricating at those labs. Under training, for the quantum software training, we've led various workshops and hackathons in partnership with a lot of companies, universities, and even consortiums. Three of the most important workshops that we did, one was last year with Pascal. It was based on neutral atom quantum computers. It was for free of cost. The registration was free of cost. You would come in, learn about what and how neutral atom quantum computers work, solve a small problem as a part of the hackathon, and then finally win prizes. The second is the quantum technologies for non-techies. It is a pretty new workshop that we have launched, and we are bringing in this workshop for people who work at the C-suite level. That is, those who somewhat know about quantum technologies but want to formally get introduced to it, but at a higher level in their organization. So that particularly when I say non-techies, I mean people who are working in HR, finance, procurement, IT, and other places, but they have to deal with, or at least deal with, one or two quantum technology related terms in their day-to-day lives. And finally, we led QSciTech Quantum BC CMC workshop on quantum machine learning and quantum chemistry. This is done in collaboration with NSERC consortiums in Quebec and in British Columbia. For quantum hardware, I would say the most well-known workshop is Build Your Own Superconducting Quantum Device workshop. We recently concluded this workshop in Waterloo last month. And as a part of this workshop, we teach you how to design, simulate, and test superconducting devices, quantum devices. Along with that, we provide you access to various CAD tools, and we can also take in your submissions for fabrications. And once the fabrication results are out, we'll send you those chips back to you so that you can keep them as a token. But yeah, these are pretty nice workshops. And the other is Silicon Quantum Photonics workshop. It works in a similar way as a superconducting workshop, but for photonics. Now, how do we actually provide these quantum services in a cost-effective manner? We branch them out into 3 phases. The first phase, or phase 0, is ideation and roadmap. If you, your academic, your supervisor, or your company has an idea but would want to lay out an entire roadmap of how a particular algorithm or how a particular device could be made, you can come have 1 or 2 day workshops with us, or come and sit with us in some meetings, and we can help you design all of the roadmap and ideation of what can be done on which possible quantum hardware or infrastructure it can be done. Second is the proof of concept. Once the roadmap is built, we can then move on to building a minimum viable product with the available quantum infrastructure out there, which we also have access to and can provide you with a cost-effective access to. And in the second phase, or the final phase, once the minimum viable product is developed, we can help you scale it on a commercial level. We can provide you with ideas and get you in touch with other companies or labs that can help you achieve commercialization. In more detail, for ideation and roadmap, as I mentioned, we have Quantum for Decision Makers workshop. This is very similar to the Quantum for Non-Techies workshop, where if you do not come from a quantum technology or quantum information background, you can come attend 1 or 2 of these workshops and then understand how quantum technologies are built from ground up, what different hardware suits your business end product the best, and which algorithm you may or may not want to work on. And these workshops include cover all the different areas. For example, overview of industry use cases, strategic opportunities that you can look around, and potential business advantage in quantum computing tailored to your company. Moving forward, in the first phase of proof of concept, we go from building a quantum software roadmap to actually building the quantum algorithm with you. And along with that, we fully participate with your team, do a collaborative R&D, and build the quantum algorithm that you wish to. And all of the collaborating R&D, all of these steps included in that are solution scoping. That is, we would look if you have a machine learning problem, or if you have an optimization problem, or if you want to use some variational algorithms, or is it purely quantum or purely classical. Then help you through with algorithm selection, development, simulate all of those algorithms or minimum viable products on the best available simulators out there. And then also finally decide if that algorithm can be or cannot be or must be run on a real hardware device. Finally, after the quantum algorithm development in the demonstrate and scaling phase, we use the simulators or the real quantum computers to run the project or the algorithm and provide you with all the results and a final report. After which, based on that report, we can see if that technology can be commercialized to a larger scale or not. Sorry about the repetitive slide. Next, for the quantum hardware prototyping, through Fabric, we have access to a lot of CMC optimized CAD tools in collaboration with a lot of companies out there, particularly ANSYS, Siemens, SoftMIMS, and more. And we provide these tools to you either free of cost or under our membership to facilitate the design, simulation, and validation of the quantum hardware or the quantum hardware product that you wish to design. Along with that, we have various process design kits, decision rule checking systems, and we have various technologies, including photonics, microelectronics, and aluminum and niobium-based superconducting devices that we can help you build and fabricate. First simulate and then fabricate. Awesome. Next, I just want to highlight the quantum computing infrastructure that we have access to. Currently, we provide an indirect access to the cloud providers from IBM or Pink in Canada. And as a part of this, if you have a project that you wish to run on either of these quantum computers, the IBM ones or the IBM Quebec computer through Pink, you can come up to us. We can run these projects through an indirect access models, and we'll provide you the results back without any added cost on it. And a major one of the important things that I want to highlight here is the quantum sandbox project or challenge that we are coming up with under the Fabric model. And under this model, instead of providing this indirect access to IBM or other quantum computers, we would provide you enough funding for your collaborative R&D purposes so that you can directly access various quantum computers out there. And what we will go through during this sandbox quantum challenge program is that we would sit with you, design your algorithm, make sure that it is exactly simulated in a fashion that it would be implemented on the quantum hardware out there. However, this would be a direct access model. We would sit and only adjust the algorithm development with you, but it would be your responsibility to run that algorithm on the available quantum hardware. The available quantum hardware could be maybe AWS, Rigetti, Pascal, and more companies. And under this challenge, you would have to apply, submit an expression of interest. Once your algorithm gets developed, we would do a collaborative R&D on it. And once your algorithm is good to go, you would go ahead, run that on the quantum cloud infrastructure that you wish to have access to. And we would provide you funding in order to get access to those cloud infrastructure models. But just a note that all of the quantum computing infrastructure is only available to Canadian academics and small to medium scaled enterprises. Through this quantum computing infrastructure, we have, since 2020, completed 35 quantum computing projects in various areas and application areas, along with a lot of different universities out there. Your university may be in here as well. Yes. So coming to the end of my slides, I just wanted to highlight the Canadian Semiconductor Symposium that we're doing next week in Vancouver. And along with the accelerated CSS, we have TEXPO. TEXPO is a funding method or a graduate research competition, which provides you with a funding once you submit your graduate project ideas. So if you did not submit any ideas this year around, maybe you were undergrads, or next year if you are graduate students and you have good project ideas in various application areas, such as photonics, MEMS, or even quantum computing, you can apply to TEXPO and get cash prizes. With all of that, this is my team at CMC Microsystems. Although I come from a software background, if you have any hardware questions, you can always reach out to Luke, Charles. Charles gave a presentation last week as well. And for other reasons, for software and stuff, you can contact me or Bruna. And that is about it. Thank you so much. Let me know if you have any questions. Yes.
Are some of your graduate competitions strictly graduate, or are you allowed to participate in them even as an undergraduate?
I think the Texpo is particularly a graduate research competition because we look into what you're doing as a part of your research under master's or PhD with some supervisor. But our workshops, on the other hand, do not differentiate on graduate or undergraduate areas. So you can still apply to workshops, and workshops also come along with prize awards. In any case, it would be good to just reach out to a generic CMC email and then confirm those details. We may make certain exceptions in some cases. Yeah.
Follow-up question.
Yes.
So out of all of your workshops, which one would you say is the most approachable for an undergraduate to attend for the first time? And can you also please repeat the question in the mic for the online participants?
Okay, yes. So the question is, out of the workshops that CMC organizes, which of those workshops are most approachable for an undergraduate student? I would say most of the quantum software workshops are approachable by undergraduate students because they start with a prerequisite of just knowing, let's say, linear algebra or some part of quantum physics, and maybe a little to no amount of Python. But if you don't know Python, you can let your instructor know that you do not know that, and we can still help you build on Python before you even start with the workshop. So they're all pretty new. I would say except the quantum technologies for non-techies, because that is completely aimed towards C-suite people. That is people who are in the decision-making process in the company. So it is not for students. Rest of the workshops, for quantum software, I would say I would, in fact, encourage undergrad students to apply to these workshops and become a part of them. For quantum hardware, I've only attended the quantum photonics workshop. And mind you, I attended the quantum photonics workshop as a grad student with no background in quantum physics and no knowledge of what quantum photonics is. And I would be very honest when I say I learned a lot from that workshop. It is all about how much you collaborate with other people in the team and how much you interact with other people and ask questions. Simply let your instructor know that these are some areas that you do not know of. And these are particular areas, if they have any resources on them, they'll share those resources with you beforehand or before the workshop even starts, so that you can simply read those resources and come up to a level to match the grad students there. So I would say Silicon Quantum Photonics Workshop, but if you have also attended the Superconducting Quantum Device, those are pretty much the same workshops. No problem. Yes.
So I do not have a graphic, and right now I am most of my quantum projects are not in like the work experience, but are the form of award-winning projects. How can I leverage these to get my new opportunity both in like software or like organization?
Awesome. So the question is that you do not have a graduate degree yet, and most of the projects are, I would say, very fundamental, but how you can
None of them are my employment.
okay, so it is just an academic experience in quantum computing, but you do not have an industry experience in it. Awesome. So first of all, these workshops are provided in collaboration with the industry. So I would give you an example of the Pascal CMC virtual workshop and hackathon on quantum computing with neutral atoms. The topics for this workshop were entirely organized by Pascal because they wanted people to know about how the neutral atom quantum technologies work. So even if you do not have a background in any of these quantum technologies, these workshops work towards introducing that concept to you. And a part of this workshop was this 2-day hackathon where you were given a problem by the industry partner that you had to work on. And along with the industry problem or with the industry partner, you also had sessions where you can go back and forth with those partners and discuss your solutions, optimize them along with officers from the industry, and then win prizes on it. And the part that I really liked about this workshop was the project at the end is something that is industry approved, not formally, but informally, you know that in industry, working with neutral atom quantum computers actually likes your solution or is, I would say, optimal about your solution and positive about it. You can publish that solution on GitHub or maybe share that on LinkedIn and have that built as a workflow from bottom to top.
This happened like twice. First case was like with Romanian 2024, and I led the project which uses Zen English and heroes. I've built like a convolutional neural network there for detecting like defects in webs. So this is like what I have done so far of that project, and I'm one of the 7 teams to get this Romanian grant out of like roughly 162 submissions. The other one was also by like the Romanian 2025, and it uses D-Wave's quantum computing. So both of them are Canadian technology, Canadian quantum firms.
Right.
Canadian, got to be Canadian, and I also like managed to make it to the finalists, and I actually placed second in this presentation. Both of them are Microsoft. So would that be like a great asset?
Yes, I would say yes, because having them on GitHub means you're open sourcing them and you also give access to other people to come and look at your projects. But on a personal note, I would say try to add them on your resume or CV as well, so that when you're applying, people know that you have these projects out there, and provide links to them so that they can just do a one click and actually go and read your project.
That's
Okay.
actually, I actually posted the second one on YouTube as well.
Oh, that's very interesting, because that becomes a part of the documentation, and having a clearer explanation of your project along with like a good documentation is something your interviewer would definitely like to see.
Yeah. The other thing is I actually like started like YouTube series. Something called Quantum Odyssey, which is a game.
Okay.
That's themed around quantum computing, and the objective is to arrange the wires, colored wires, in such a way that the balls split and merge.
Mhm.
Merging, splitting, color changing balls have to match those one. And patterns of the puzzles, you're only allowed to like use certain of them, and they work in exactly mathematically identical way as
Mhm.
the unitary model quantum computation. So I'm actually the top IRA scene, and I actually got in contact with the founder. So, and that like after the end of this, I'm going to like later recording of the last few puzzles, how people solve.
How sorry, but in the interest of time, I'm just gonna let some other students ask questions if that's okay.
Okay, sorry about that.
Yeah, I would just like to add one thing, maybe think of publishing a paper for that as well. It would give you a better traction on the project if it's unique, you think. Yeah. Any more questions? Yes.
If I'm not mistaken, you said one of the things you also did was try and reach out to companies to adopt quantum technology into their work.
Yeah.
Are they certain sort of industries, companies within, like, are they certain industries that you target, and if so, why? And have you also noticed certain industries be more willing to adopt quantum technologies than others? And again, like, if so.
Yeah, that's a good question, but I would say we don't actively reach out to companies, but we have, through these workshops, encouragement to those companies that they come and adopt these quantum solutions as well. But we do have certain projects where we do have students reach out to different companies that are not using quantum solutions to particular problems, maybe like HydroQuebec and stuff, but I don't want to name them. I'm just giving examples out of my head that maybe they could have something in quantum applications that is useful to them. And if they're willing to collaborate with CMC, then we can have them do that project with us, or have like an academic partner as well that can do that project through CMC with that particular organization. But yeah, the main problem is finding utilizable enough applications or real world applications that the companies are willing to invest in and to invest into the R&D process to look into if they can get something out of that project, like get some minimum viable product even. If that is not possible, then yeah, unfortunately, the companies do not want to invest in that particular technology. No problem.
Awesome. Can we get another round of applause?
Sorry. All good. Thank you so much.
Couple last notes I want to add. I promise I'm not paid by CMC, but the workshops that they give really are awesome. The hardware workshops, both the ones that she mentioned, the quantum photonics and build your own superconducting quantum device one, were huge inspirations behind the numerical and ANSYS HFSS problems for this event. So I would highly recommend it, no matter what year of your studies you're in, you should go check them out. Some things she didn't mention is the attendance fee is also heavily discounted for students. So yeah, anyway, with that being said, I'll pass it on to Mehdi Bozoré. I will just get your slides up and ready. Oh, what happened?
Yeah.
Sorry, just a minute. Okay. Oh, I think I might need to restart sharing my screen. Duplicate. Okay, there we go. Okay, perfect. I think we're good now. Okay, here you go. If you want to start with an introduction.
Thank you very much. So everyone, first, thank you so much for the invite. My name is Mehdi, and I'm a founder at Quantum Advantage Partners, or QAP. So today I'm going to talk about basically one big question. How do you turn complex tech into real-world impact, which is basically the main problem of every single startup in quantum. And before that, I'm going to start with a quick, basically, history. So what's my background, actually? So I studied with some nice, interesting academic foundations, actually in France, basically mathematics, computer science, and then I did focus on physics. Basically, that gave me the tools in order to think in models and systems, from fundamental physics to computer science. So basically the mathematics to actually describe something, the model, physics, so where you do extract it from a nature point of view, and also the computer science to model everything and look at the evolution. Then I came to Canada for vacation and never went back to France. That was actually a good move. That was a really good move. So I landed in Montreal. I think it was like 1998 or 7, something like that. So long time ago. I did another master's degree at University of Sherbrooke in theoretical physics. That was actually quantum mechanics. Then I worked for the HPC Center at the University of Sherbrooke, And I have to say that one thing that comes over and over and over again is I was extremely lucky all along my career because somehow I ended up at the right place at the right time. So University of Sherbrooke, the HPC Center, right place, right time. We got like massive funding from the government of Canada to build basically HPC infrastructure. I was in charge of the basically design, deployment, and benchmark of what ended up being like the most powerful parallel cluster in Canada for a few years. So good. Then I got a bit tired of just academia. So, okay, let's go somewhere. So I ended up in Toronto working for, actually it was SMB doing high performance computing software called platform computing with lots of customers, especially in North America and in the US, all about cluster management and workload management. So I was there for like a few years, like super technical work, basically a developer doing integration of mass library on HPC clusters. And then this company got acquired by IBM. That was pretty cool because at this time, IBM basically was the king of HPC. And so what I took from that was a complete switch in a career, going from like super technical to actually business. So going on a dark side, as some people would say. And I did something I always wanted to try, like influence product management. And one thing that is wonderful at IBM is that you have all these training tools available to completely change career if you want to. So product management, offering management. And then again, I was so still in the HPC business. And then I was super lucky, again, right spot, right time. IBM started to put like those little QPUs on the web so people could play with. And I was like, wow, awesome. I'm going to do one thing in my life, demonstrate to my parents I was not completely stupid to study quantum mechanics, and sometimes maybe it might have an impact on people like in their real life. So that was actually the beginning of basically quantum computing, like super cool. Lots of things I loved at IBM, the concept of quantum ambassador first. And actually that's key in the creation of QAP as well. Like you can't have people talking to, as Sasha mentioned, C-level people about quantum if they don't know what quantum is. And basically you have to have people with scientific background to talk about technologies based on science that might have a massive impact tomorrow. So that was a big thing. Then I did move completely to IBM Quantum, offering manager for the IBM Quantum startup, actually. So that's why I basically know all of them, the historical startups like QBraid, for example. Then I got a bit tired of being stuck to only one modality, and my big thing is software. So I left IBM and joined a startup. So that was beginning of the pandemic, lockdown everywhere. So that was Cambridge Quantum Computing. And that was not easy, pandemic. Plus, we were going through a funding round and our chief business officer resigned. So I got a phone call from the CEO and Mehdi, are you up to it? Yeah, no choice. And so I did. I had to work on a very interesting problem. I love problems, especially if I can solve them. And in this case, the problem was, how do you, from non-dilutive funding, so at this time, lots of quantum projects, especially on the algorithm side, they were sponsored by public money. But how do you go from an engagement, this type of government-led engagements, to actually build something, extract the IP, and make sure that you can reinject this IP into, let's call it proto product at this time. And then what would be the plan to, throughout multiple engagements, and this time it was like not only non-dilutive funding from basically public money, but also like full commercial engagements, keep not only extracting this IP, reinjecting it in your product, but actually you're building a product with functionalities. And that's very cool to have it based on paid engagements, because it means one thing, like you are right on target. And in my work of product management, you always have to go through like all kind of studies, market studies, and then interviews and everything to actually find out what is the functionality of the product that people will pay in the future. In this case easier because people already paid for it. But then the second problem that comes along with this one is, wait a minute, you completely need to change your structure because you're selling engagements today, but then same people will have to reinvent themselves into product managers and equivalent roles. So not only you need to extract something, re-inject it in your products, but also completely change your team. So that's change management. So interesting problem. Then CQC did merge with Honeywell Quantum Technologies. So that was basically IBM number 2, different modality, trapped ion. So I left after a nice discussion with someone I knew at the Quantum Algorithm Institute in BC. So still the pandemic, but not as bad as with CQC. So I joined QAI. The challenge in this case was completely different. So in BC, the industry is like really interesting, and it's a wonderful, actually, industrial environment, because you have mining, you have all these like hydrogen politics that are pushed by the government, and you also have all the transportation industry. So lots of actually industries that were tagged by everybody playing quantum as, yeah, they will benefit from quantum big time. But at this time, at least, those industry players were absolutely not aware of quantum. So they had no clue about what quantum was and what quantum could do to them. So part of my job was to make sure that these big players know exactly what it is and actually start engaging with them. The other problem that basically had to be solved, skills, like those HQP that Sasha was talking about. I mean, you don't come up with HQPs like bang tomorrow. No. It comes from universities and students. You need to have the programs. You need to have actually at those students, you want them to be like super skilled on quantum. Do you have startups that can hire those students via my tax programs? If no, well, then that's a problem. And the idea was actually to get those skills from other provinces, bring them back to BC. So then it's the snowball effect at the end. Then I had a chat with another person I knew. Then yeah, in my career, it's all about having a chat and then changing job. But the problem was super interesting as well, because so I did touch about superconducting qubits, about gate-based quantum computer, about like those talks with the industry. But then the company was multiverse computing, and their problem was, so first, yes, they did pure quantum gate-based, but they also did non-gate-based and actually playing with D-Wave. And one thing they did, and they're still doing it, on top of it was quantum inspired. And I can tell you, at this time, quantum inspired, that was not well seen by lots of people. But I was like, yes, come on, that's the solution, because the problem with the industry is the gap between whatever they have today, HPC mainly, and quantum, it's like science fiction. And the jump is so big, like, so first it's tagged as super risky and potentially super expensive. And yeah, so that's why most of the decision makers in the industry looked at quantum like, you know what, let's wait 5-10 years. But quantum inspired, that's very cool. You do leverage quantum something. In this case, it's all about correlation mainly. But whatever you run, you can execute it on classical hardware. So that's not a simulator. That's even better than that, because the technology was and is still tensor networks that can be applied to many, many areas, including neural networks. you can actually tensorize neural networks. So with a technology that is quantum inspired, and then what happens is you can shrink your neural networks, which means you get two main things. First, the training phase is you can reduce it, but when you do so, then what you save is money on your energy bill, which and you can say that you are greener than other technologies. So that was multiverse computing, and the challenge was to move from those consulting engagements, to actually build the product and actually sell the product. So it was a big change from a process point of view, more on the sales side. Then I had another chat with the previous CEO of the Quantum Innovation Zone in Sherbrooke, and said, you did a pretty good job at PQC and QAI and multiverse. So what about instead of having to deal with only one entity, basically I give you a bit more complexity to deal with. And in this case, you will have to come up with solutions for an ecosystem. So I started to scratch my head and you know what, that's challenging. Okay, let's go. So that's when I left Multiverse to go to the Quantum Innovation Zone in Quebec. And then the challenge was, that was an ecosystem play, but one big problem was, so the way the Innovation Zone is structured, so it's funded by the government of Quebec and pieces from the federal government as well. The zone had projects. The first project was called Espace Quantique 1, which is a nice building, office space, sorry, and also a lab. But what was a bit unique at this time, or at least at the beginning of the story, the lab was a shared lab. So what it means is the government will give money to the zone to buy, for example, dilution fridges that can be rented out monthly to startups. So you solve one massive problem in this case. Like, what quantum startup has enough pre-seed or seed money in order to be able to buy a 1 million dilution fridge by themselves? That's just not possible. When you lower the entry, the cost of entry that low, it means that almost any student who has a very good idea about quantum hardware can actually find a way to start his company. So that was the main goal. And then we did photonic lab and other things. So I used this framework to actually not only solve the problem we had to solve, and that was, so once you rent out everything, basically all the office space for startups and all the equipment, then you reach a cap. The only way to increase the revenue is, so either you make it pricier, so not good for the startups, or you extend the footprint for both the labs and the office space, but then you need money. And one of the mandate that we had was from the government, okay, guys, we gave you money, but at some point you need to be like independent financially. So basically it's rented out at costs. And then the question was, where do we get that money from? It's absolutely needed if we want to survive, basically. So that was my problem. And I came up with basically a structured membership in order to completely decouple the revenues from the actual physical infrastructure and create new revenue from this membership. And then it was quite challenging because you need to sell something that is not tied to an actual infrastructure. But so I did the design of the membership and then executed on it. And yes, we were able to sell. And the idea was that we will be selling the value to players. So for example, the startups who are far away, cannot come to the office in Sherbrooke right now, but want to benefit from the advantages that you have from being in the zone membership. Enabling technologies provider, typically USMB, who's been on business for 10, 15 years maybe. Quantum is a new market for them. And what is priceless is to get feedback from startups about the hardware. They are new hardware. They are in the process of designing. Okay, you pay, and then you put your new hardware for testing in our lab. So then the startups will test it out and give you feedback. Wonderful. And then the large groups. So the large group, large companies, typically Global 500. So it works two ways. The startups need those large companies to get like POCs and things like that, and also the visibility. Like, oh, I'm so good, my techno is so good, I did a POC with, I don't know, Airbus, for example, or Volkswagen. But at the same time, Volkswagen absolutely need and love to get insights of what's coming tomorrow, and that might be useful to them. So the idea was to organize those like reverse pitch events, where basically the large company comes with their industry problems, like, oh, I know I have to solve this problem. That's a big pain point in my industry. I think that quantum can do something for me, and then expose the problem. And all the startup pitch basically their solution to this big company, saying, you know what, we did not solve your problem, but we did solve a similar problem for another client in Asia, Europe, or North America. And then, so that was the second part of the membership. And then who's playing in those like innovative ecosystems? So of course you have academia. And of course you want as many academics part of the game, because that's typically the people, the supervisor who will have their students part of a MyTax project for a project between industry and the startups. So then it benefits on two sides. And the last one was my multiplier, the industry associations. So instead of talking about quantum to, again, one specific company, even if it's a big one, then what's even better is to arrange something with, I don't know, Electricity Canada, for example, and then you pitch quantum to 15 big players in energy in Canada. So putting everything together was, so that was one of my solutions to the problem. But then I realized at the same time, so quantum was getting better, and one thing happened, ChatGPT. So the rise of those like LLMs. So at the beginning, I was just, okay, so let me try this out. Wow, that sounds like science fiction. And then I started to use it like just more and more, like pushing it. Like I have the feeling there's something, and let's push it. And after like 1 year and a half, basically, so I did deploy all the Gen AI tools at the Zone, basically based on ChatGPT. And we had like, I used it like for every single step of lots of my processes. And that gave me the feeling that actually all those processes, like business processes, so something as simple as I'm looking for something for one product, I need a market study. That market study doesn't exist because it's too niche. And anyway, people building those market studies will call me or my friend to get information. But like these deep research tools, for example, that came online not a long time ago, were absolutely perfect for that. So one thing. And then the pitching questions back and forth between the LLMs and myself, like testing ideas, like starting to use the more advanced they became, like using them as a sparring partner from on the strategy side. So gathering data, strategy, and then writing things. I mean, they are way better than me to write something. And for one good reason, they have instant access to context. Like, for example, I had my strategic advisor at some point with the context of the entire organization, like strategic plan, all the presentations and everything, and having ChatGPT to draft me the beginning of my pitch for like whatever conference. That was way better than me, because it was able to actually take everything about the organization and put it back in this speech. And then I continued to push and push. So I tried all of them. And another problem that came up was actually about not my position, but the type of positions that I had, like at CQC, at District, and at Multiverse. So basically, and we're not that many, to be honest, like experts with one leg in science and one leg in business. So basically, scientifics, like people from academia, some of them at least, will say, Mehdi, yes, it's to business. And then when I talk about something with business people, Mehdi, come on, it's too scientific and not business enough. So basically, it's very nice to have one leg in each area, but you will never satisfy anyone. But actually, that's pretty cool because you can play both sides. So you can augment the business with something that is scientifically grounded, and you can enrich science with something that is grounded, but in business this time. So not lots of basically this type of people around the world, especially in quantum. So there's more and more in AI, for example, but not that many in quantum. And then, wait a minute. So I love startups. I mean, we need to do whatever we want to, all of us, to make sure startups succeed, because that's where the innovation comes from. But lots of startups would love to have an expert. And you can see that today in the AI world. Like everybody wants like the AI expert, and they will actually put an insane amount of money on the table. And that's also part of the problem, because the entities who need the most this expertise are not the entities who have a lot of money. So they cannot afford this type of expertise. Only the large companies can. And the solution to this problem actually is something that is well known in the industry for like a few years now, is fractional executive. So basically, instead of getting an expert executive, then you get a fraction of it, like a part-time executive. But it's different than consulting. Typically, a consultant will give you the strategy, and then the strategy will fail, and then, no, the strategy is good. It's execution that is a problem, not my problem. When the fractional executive is not a consultant, is like deeply involved in the company or not for profit, whatever it is. So he's also accountable for execution. So that's actually the why I came up with my own company, in order to solve this type of problem that cannot be solved within organizations or company. So everything did converge actually a few months ago, because I registered my company in early September, and it's not easy, not at all. That typically means ingesting quite an insane amount of coffee, not sleeping a lot, and working like crazy. But it's totally worth it. So, and actually, why, at the end of the day, why QAP? Again, like for many, many years, I saw like so many times, and especially I worked a lot with CDL, for example, and Privé Studio in Quebec. So like startup mentoring. Super duper teams, great science, but the problem was the unclear underlying story. Let's put it this way. So basically, how to translate the super duper science into something that is understandable by non-experts, and move from, oh, that's very cool, like a super cool scientific project, to someone will actually pay for it because it's quite, and it's not only the money, because when people pay for something, it means first they find it useful, and then it has a price that is typically in the industry tied to the pain they are feeling and that you solve with your project or product. So the main idea also was what I just described before, basically break business processes into the basically atomic level. So what's the information that is in this process? What are the questions that are attached to this information, questions that you need to build the entire process? And also, of course, what are the decisions that are part of this process? And my idea after, as I said, I played like an insane amount of time with all those LLMs, how to actually put AI at the core, like rebuild. So first, completely destroy the process, break it down to like the most atomic pieces, and then how to reinject AI at the core and rebuild the process from ground up. And that's exactly what makes the difference between maybe 1.0 before all these LLMs and maybe 2.0, which is like I can do 2 times more work now than I was able before. And it's kind of similar to quantum. What is the most interesting piece is not the fact that I'm more efficient, like I do stuff quicker. No. The most interesting part is I can do stuff I was not able to do before. And actually that's key, and it's the same for quantum. So now what I do is I'm using like all those processes to help deep tech and quantum teams to actually translate the science. So you can see me as a translator, nice. But translate this science into something that's understandable by the business, that has a clear value attached, so people can actually invest in it. That also means that you de-risk the process through this story. So clear narrative. And what is also super important, that's one thing I experienced starting at actually before IBM, like applying all the engineering and especially software engineering techniques. And yes, Sasha, you know those ones, like agile. But agile not for a software team, agile for biz dev, agile for marketing, and all that stuff. So basically, you take the best process available, and again, you break it down and you inject it when and where it can fit. So that's kind of the whole idea. Now the engine itself, again, you break down everything, rebuild that as AI native. So what I mean there is a very basic example would be a decision process. So decision process, those like mathematical, like MCDM models. So you can come up with quite interesting and complex, at least from a mathematical point of view, MCDM model that will represent the decision process that you have, like even a business decision process. That's painful. That's painful. You need to code, you need to, it's very complex, it takes time. And yeah, okay. When you use like Gen AI tools and LLM in particular, you can let it do it. Like you don't have to actually write an insane amount of code, go through testing and everything. You can actually describe exactly what you want to be done and how you want it to be done. And that's actually key in the process. And of course, I mean, nobody's perfect. Physicist by training. So when I play with those tools, when I find something, my first reaction will be, okay, wait a minute. First, am I hallucinating or not? And then is that thing that I just found interesting, is that grounded in science? And it happened to me like at the beginning when I started to use LLMs to score stuff. Actually, that's called LLM as a judge in computer science. And that's a field that's research. Lots of people are working on it. So it's really grounded in science. And that's my main point as well. I don't do stuff that is not grounded in science. And then once you're done, like rebuilding a process, then you can turn the insights into, again, narratives and those concrete like sprints. Actually, the 30, 60, 90 days story is actually sprints. from business point of view, from sales point of view. And that's what I did implement at the Quantum Innovation Zone as well. Like the revenue team had, I think it was 4 weeks sprints. Like in this sprint, we would, for example, hey, implement the dashboard for the CRM, or come up with the beginning of the strategy for blah, blah, blah. Then again, from classic to AI native. And that's where I found it's okay, similar to quantum, because the idea is, so you cannot basically just translate your classical algorithm into a quantum algorithm. That doesn't make any sense. It's a completely different paradigm. And so no. So what you need to do is you need to look at the problem. You need to look at the problem, but need to look at the problem at its core. So what is the mathematics behind the problem? And then once it's done, so any industrial use case, in fact, at the end of the process, if you go through this, and you have to go through this methodology, it is a mathematical problem. So, and you also have classes of mathematical problems. That's what I explained about the startup, saying we didn't solve your problem, Mr. Whatever, Volkswagen, for example, but we did solve another problem for another client. And the problem that we solved, when you extract the underlying mathematics, it's part of the same class of problem. So what it means for Volkswagen in this case, or wherever it is, it's like, okay, wait a minute. So I started from something that's super risky, like quantum, nobody knows what it is exactly, to something that's way less risky, because then I have someone telling me that he or she did solve the same type of problem, but not, they just don't say it. It's mathematically proven. So all of the sudden risk goes down, which means like, oh, basically the possibility of investment goes up. And then, so you look at the problem from a different angle. That's the quantum way of doing things. And then you rebuild a new algorithm based on what you're using right now, which is quantum. Then real life, what does that mean? Two examples, startup diagnostic. So instead of having 3 people basically going through like applications and everything, no, I send out basically a questionnaire that the startup can fill out even like partially. Then I have an interview with them, and LLMs basically extract the info from the questionnaire, extract the info from the transcript of the meeting that we have, plus some deep research stuff about their products and the startup itself. And then with all this information, they do score it on multiple dimensions and build reports that basically will tell the startup and myself, okay, guys, your strengths are this, and your weakness is this. What does that mean? If you want to basically raise and be more appealing for an investor, for example, you need to fix A, B, and C. And then we can reorder A, B, C. So you can fix the low-hanging fruit first with like something like 4 weeks work. So that's one thing. The second one is actually that's the most interesting, and that's the one I've been working on lately. Is let's say you have pitch deck that you want to pitch to investor, or a big project that you want to submit to a governmental entity. So you would love to get feedback from those basically business functions within government or whatever it is, but you cannot ask them. And first, because they are not available, and also because you are going to pitch to them. And the idea is whatever you want to pitch, if you get it reviewed before submitting it by something that will represent the same decision process, like what I was talking about before. So if you can rebuild this decision process and apply it to whatever you're working on, then you can get feedback on your work before you submit it. And that's exactly my multi-view panel assessment. I can actually pitch a pitch deck, and I did it for myself. I was the first guinea pig, actually, to multiple personas that do represent the decision process from a business point of view from multiple entities. And that works extremely well. So that's very cool. Now, what can you steal from all this? Don't start from the tech. Tech is cool, don't get me wrong. Start from the change. Basically, ask yourself, okay, I have a brilliant idea, but what will this idea change in everybody's life if deployed, for example? So that's one thing. What I call the multiple lenses as early as possible. And by multiple lenses, what I mean is multiple point of view. So whatever it is, your research project, for example, try to re-explain it, not only to a scientist, but to your neighbor. Actually, I ended up with a broken engine on the 401 at like 11 p.m. between Montreal and Toronto. And the poor guy who told me back to Toronto had to endure my quantum speech for like at least 1 hour and a half. But he knew everything about quantum at the end. So that was interesting. My dentist as well. Then, and then the last thing I would say, think as an augmented leader. I mean, those tools are not magical. They are helpers. They augment basically all you need to make a decision. Like, again, as stupid as deep research with ChatGPT, you get more information. And if you make sure that there's no hallucinations, then it's grounded information. So you have more to decide on. That's what I would say. Structure information and question. And again, use, in this case, human time, for interacting with people, because that's also the way you get the most useful information. And that's it. And I was over time. Any questions?
Cool. All right. Thank you.
I guess it's not. What has been, like you said, you sort of transition from first solving scientific problems to business problems, and this is what about like the satisfaction of problem solving? How have you found that difference between solving scientific problems and solving?
That's a really good question. Oh, okay. So if it was, okay, the question is, okay, I did solve scientific problems, I did solve business problems. Which one of them is the most satisfying? Actually, I would say both. And there's no difference. Because at the end of the day, it's a problem that you need to solve, which means you will have to learn everything about it. And learning about, I don't know, theory A, B, or C versus learning about pain points, specific pain points for industry. That's extremely cool as well. And at the end of the day, that's a mathematical problem. So that's good.
I guess another question is, how come you decided, why exactly you decided now was the right time to start with?
That's another very good question. Feeling, I would say, gut feeling. And actually, the funny story is an insane amount of my close friends from IBM and other companies that I really trust because I really think they are really good. All of a sudden, I was like, oh, wait a minute. Everybody is starting his own company. And it was always the same pattern. Like one-man show, at least at the beginning. And talking to all of them, it was exactly this, exactly what I just said. Like there are problems that you can solve within an organization and problems that are not solvable within an organization. And all of us also run into the same issue. Like, and IBM said, drink your own champagne. So basically, when you're an organization, whatever it is, promoting innovation, and actually your goal is to make sure that innovation is adopted by the industry, you have to be the most innovative person. Because if not, it's like I'm going to buy Tesla. So I have a wonderful chat with the Tesla sales guy. And at the end, when I'm about to sign a check, I ask him, oh, so I guess you drive the latest and greatest Tesla. And then the guy tells me, no, I have a crappy old diesel truck because it's cheaper. And that's what I bought like 10 years ago. So you cannot have this type of answer. And what I found, and some of my friends as well, like that's still the answer. So the only way to solve it is, you go on your own and use the most innovating tools that are available, and then reinject it in whatever you do.
I guess kind of piggybacking on that as well. So starting off, I know you said kind of stress us, so your ability in the company is Medi 2.0.
Yes.
And so it starts off as a one-man show, and then it grows. How do you envision, like, and also you said what it kind of is like is translate scientific problems into more like, I guess, marketable business.
For the translation part, it's translating the scientific narrative into a narrative that is understandable from a business point of view. It's really, at the end of the day, to be honest, it's really language. It's language, and what I mentioned about like the multiple lenses, it's also different point of view. Like I saw that so many times in meetings with startups presenting something to a company, like, oh, look at our stuff. It's like 10 times more precise because of blah, 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 blah. And then the person on the other side was like, and how long do you need for that stuff to run? Oh, it's 5 times slower than the classical solution, but we are 10 times more precise. And then the business, let's call it business person on the other side would say, yes, but you know what? In our industry, we don't care about the precision, the additional precision. What's important to us is to be as quick as possible. And it's like, oops. So making sure that there's a one-to-one mapping between the solution and the need, actually, and the usefulness. At the end of the day, that's what it is.
How, in the interest of time, one more.
Okay.
Yeah.
Sounds good.
Okay, so I would like to welcome you all. I am Clarissa. I'm one of the organizers of this event, and I would just like to extend another very big thank you to the three of you for coming and presenting and being with us here today. So I think we are working with one microphone, so I will be asking some questions and then passing it over to the three of you, if that would be all right. So I'm very pleased to welcome, as you all know, Sasha and Mehdi and James. So for the first question, I'm going to get you all to answer this. In one sentence, what does the future of quantum mean to you, and what specific gap in the quantum ecosystem is your company positioned to fill?
The future, I guess, is application-specific uses for quantum, so not one size fits all. And we'd like to position ourselves as the quantum operating system.
I would say the same applications for me as well, mostly because I come from an applications background. But maybe physicists would say it's just research for them. But my company is positioned to help people who do not know quantum yet, or are at places where quantum is not accessible to them. We are positioned to provide a cheaper, or I would say a subsidized access, so that academics and small-scale startups can actually get their foot into this technology and get up and running before the big companies go ahead. So we're like a middle person helping small-scale companies, organizations to come up with better technology.
Thank you. So I'll be a bit blunt and provocative. So the future of the good future of quantum for me is one will stop talking about quantum because it will be everywhere, and we will only be benefiting from whatever it will bring. So that's one thing. But as Sasha mentioned, but like, I guess we are, the three of us, well aligned applications. And what makes sense is the combo application plus hardware, because you cannot have applications if you don't have hardware. On my side, I work on making the translation between the business side and the scientific side, making sure that everybody understands each other extremely well. And I do play both sides. Startups understand the business, but also the business understand what's the upcoming science.
Thank you. All right, so our next question is for James specifically. As we move toward more hybrid algorithms, where should the boundary lie between specialized scientific computing platforms and unified access platforms like QBraid? Should they compete or should they integrate?
So our philosophy at QBraid is always to let people work in any framework they would like to. So I think at this point, I'd say collaboration is best and not closing off, even though you do develop some sort of moat as a company if you do get people to buy in, but that's very tough. So, and as we are also, as far as the hybrid applications, we're trying to get closer to the hardware to allow people to, once again, in any language of their choice or any sort of software ecosystem, they're able to run these hybrid applications. And at this point, I think that would be more error correction, as that's where we're headed. But yeah, problem-tailored error correction, I think, is where we're headed right now.
Thank you. And for Sasha, as researchers build more complex hybrid quantum classical applications, what is the most significant software challenge you see in managing the workflow and data between the classical and quantum processing units?
I feel that's a good question because this is where the current problem stands, that you have two different, or let's say more than two different architectures to move back and forth between. And the amount of data that you're trying to flow becomes difficult. First, to change that data from one platform to another, quantum to classical or classical to quantum, and you do not have processes that automated. You do not have processes that are in real time as fast as you would want them to be. Let's say you have certain quantum computers up and running, but you want AI included insights into what the noise model would look like, or how in real time can you do error correction. But in real time, quantum works way faster than the classical models out there. So you cannot have that back and forth without any latency. So you need to develop those architectures. And other thing would be, yes, the OS would be one of those things as well, because there are different fragments in classical computing as well that you need to join them up together. Mehdi mentioned agile workflows, and I really wanted to work on MLOps workflows in quantum, because currently if you build these workflows, like even in quantum machine learning, you have to have a lot of manual intervention without any automation. So there isn't any platform out there that currently monitors quantum processes that are heterogeneous with other classical processes, or let's say processing units. So you need to automate those things. And coming as a researcher, the problem is, since you do not have this software, you have to build it yourself. And building it means you cannot scale it beyond one project, one classroom level project or one lab level project. So I would say those are some of the problems that we currently have in software.
And for Mehdi, how do you help a deeply technical team build a compelling business narrative and identify their first viable commercial application?
Thank you. That's a wonderful question. No, actually, I start on the opposite I do it the opposite way people usually do. It's like basically, okay, let's say your stuff, whatever it is, let's say it's gonna work. So what will it change for me and for lots of people next Monday morning when we wake up? Like, what will be this change? Is it a good change? Are you basically enhancing something? And actually, there's typically two things that can happen. Your solutions, scientific based, will give people more, or they will save more. So at the end of the day, you either make more money or save money, and then you go again back, deconstruct everything, and reconnect the two narratives. So when the startup talks about their solution, they don't talk about science, they don't talk about even quantum, because at the end of the day, on the industry side, like, I don't care if my phone is based on, I don't know, a quantum processor or something else, or like a DNA computing. I want to be able to use my phone. And if I can use it more efficiently, even better. Perfect. And if I, let's say, solve a problem that has been like so painful for me for like many months, then yes, I'll pay more. That's exactly the type of things I do try to explain to the startups, so they understand and they can rebuild their narratives for the next pitch session.
I'm sure that helps keeps them very grounded. So moving on to the path to practical quantum advantage, I once again have a question for each of you. So starting again with James. Once hardware performance reaches a certain threshold, the value shifts to the software layer. But in quantum, every hardware platform is fundamentally different. Do you bet on abstracting those differences away entirely for users, or do you lean into exposing hardware-specific controls so experts can extract every last bit of performance? What path do you think creates more real-world value on the road to quantum advantage?
So, in the future, yes, you will abstract everything away, but I think that's going to take at least 5 years, probably 10 years. Before that point, yeah, we're going to need to have, each company's going to have specific tooling that they use to get the most out of their hardware, and at least in the near term, you're going to have to work with their scientists directly to get the absolute best out of it. But our goal here is that other people can at least work with the hardware without actually knowing each specific type of hardware, like pulse shaping, that you would need in order to do that. So yeah, our goal is to make it so people can get that advantage without having to change each programming language they use when they go to a different hardware.
Thank you. And for Sasha, for researchers aiming to demonstrate quantum advantage, the ability to accurately benchmark and validate results across different platforms is crucial. From your perspective, what is the largest software or methodological gap in today's benchmarking and validation tools that needs to be closed to credibly claim a quantum advantage?
I would say it is the lack of hardware agnostic benchmarks. Also, this stems from the problem that you have to use different SDKs or software development kits while you're trying to using different hardware out there. And there is no way, unless you establish such hardware agnostic benchmarks, that you can compare how a particular problem or a particular algorithm performs on, let's say, hardware 1 versus hardware 2. When hardware 1 and hardware 2 are fundamentally different hardware, you, of course, have problems in getting a common benchmark, but that is where the research currently needs to be, that you establish something on a common level, just like how you have those middle layers in software where no matter which GPU or CPU you're trying to run the software on. You can simply use just one library and get that stuff going. We need to have that for quantum as well, my take.
And for Mehdi, if you had to pick one, what is the single biggest mistake you see quantum startups make in their go-to market strategy?
Looks like I'm just repeating myself, but no, it's the same story. It's to think that the demonstration of whatever advantage their solution brings is so grounded in science, and typically at the end of the day it's mathematics, like the 10% I mentioned, like 10% more precision. But the thing is, okay, so does that matter? And the big thing is always to connect. Another example I would say, startup A solves one type of cancer, wonderful. And then the typical life expectancy of people for this country is, not good, 60 years old. You cannot die from this cancer before 70 years old. It's still good. Does it make sense, and is it worth it? No. So first you need to extend the life expectancy of people in your country, so then you can actually think about, yes, actually that was really good, and now that everybody lives longer, then I need to take care of the cancer that statistically will develop at this time. And that's always this check, this actually sometimes it's even a cultural war, but this grounded in science, but also in reality. That's what I mean.
And once we've gone from the path to quantum advantage, if we're looking at the 10-year research landscape, so I asked this question to all of you. Looking ahead to 2034, what single capability in your respective domains, whether it's fabrication, software, networking, investment, that seems impossible today, do you believe will come routine? And what current certainty in quantum computing might be completely overturned in the coming decade?
I think what will become a certainty is very unknown, but if I had to guess what might be routine, the only sure bet I think at this point, assuming quantum computers work eventually, is probably high accuracy chemistry calculations would be the only one that if they work, would be available within 10 years. Like even Shor's algorithm, I think, might need too many qubits to actually run routinely. But yeah, chemistry, there's recent work saying maybe within 10 years, you could do a very high accuracy calculation routinely in a few hours, which would be impossible today. And that might, as far as the business use case for that, that's still pretty speculative. People would have to figure out what to do with this very high accuracy data that's routine now. But maybe you'd feed it into a machine learning model. But that's a future discussion.
I would focus more on the workflows again, because I think irrespective of the area that you want to see applications, and at the end of the day, they're all just pipelines and workflows. And I feel maybe not in 10 years, but maybe more than 10 years, but you would see abstraction in those workflows that a common user or a layman wouldn't have to worry about having it implemented on a QPU or a CPU or a GPU. Like currently how it goes, you do not know if ChatGPT is currently working on a CPU or if it has some attached GPUs to suggest you answers. It's just you have a small little chat box without having to worry about the technology behind it. So I would say developers and researchers would be moving more towards abstraction for the common users. But for the developers, on the other hand, it would be more about having less manual intervention on all these processes. Having automated things or automated orchestration workflows where the workflow itself suggests you if it's better to go with a quantum processor at this particular point in the pipeline or if to use a classical processor for it. So yeah, my major work being in pipelines and workflows, I would really like to see that common user does not even need to know if it's being implemented on a QPU or a CPU.
I'm way more optimistic. Actually, at the beginning of my quantum career, I was way more pessimistic, but now I'm way more optimistic because if you look back at the past, like the semiconductor story, so semiconductor, the beginning of the quantum story, there was only one thing going on at the same time. Today we have two things. So quantum is one thing, like massive promise, but all this like AI and Gen AI, that is like that massively accelerated like almost every single process, including the scientific process. And from my point of view, that's the biggest uncertainty, because if I look at the pace of even scientific discovery, like when I was at the beginning at IBM, like every morning, yeah, let's go on archive and check what's going on. Okay, cool. I can't. Like today, I just can't. It will take me like 1 week to understand what happened yesterday. So, and it's getting, okay, I don't know if I should say better or worse, but it's faster and faster and faster. So that's why I think that the 10 years that you mentioned in your question, I think that in 10 years, basically, it's almost like turn on Sci-Fi Channel, basically, to be honest. It's what we will be able to do, not only with quantum, but with the combination of quantum and AI and whatever is going to come next. To be honest, I have no idea. Like, if you ask me, like, last year, like, about what I could do today, I had no idea. Like that's what I don't remember who I told you the story, but vibe coding, the concept, it's like February 2025. Like Andre, I always forget his. Thank you. Wonderful YouTube interview, by the way. February 2025. So I started to play with vibe code my stuff basically right after. 2 weeks ago, Google AI something. 30 minutes, I did vibe code an application, not a piece of code, an application. And then I did it again when they pushed basically Gemini 3 like a few days ago. It was not a basic application, that was an entire CRM. I asked that saying, okay, so I need a CRM because I don't want to buy one. It has to have like this and this functionality, and for the rest, like just standard stuff. And then 30 minutes later, it was like, I had something to play with that I need to correct, but that was like, no, couldn't think about that 6 months ago. Not even 1 year, 6 months. So 10 years from now, no idea. Maybe I'll have a third arm on my back because I can do more stuff. Exactly.
All right, and so I would just like to take this time and give you three the opportunity. Was there anything that you would like to speak on more today that you haven't had the opportunity to, whether it was a comment from your fellow presenter that you would like to touch on, or any other question that you may have heard in the audience? No? Perfect. Okay, and then I would like to open up the floor for a few questions here, knowing that once we break, there is pizza in the other room, and I think we have some scheduled mingling. We have cupcakes and pizza. So if there's any pressing questions. Yes.
I was wondering, we've all, I'm assuming most people have heard, I guess, just that phrase of nuclear fusion is always 10 years away. Do you think that also applies to quantum? I guess just for everyone.
Is there someone who would like to take this question?
Me? Okay. I don't know. Maybe I can. Maybe because, like Betty mentioned, yeah, even 4 years or 5 years ago, I didn't know I would be working in quantum, and currently, although it does seem that finding an advantageous use case is pretty much of a, like, not one hand away, more than that away. But you never know. Someone may come up, vibe code something, and you may have some possible enough utility or good enough advantage for it. But yeah, for now, breaking all the myths here, I would say yes, it would definitely take some more time to find a good advantage, because utility, or I would say applications, again, depend on the kind of hardware you have. And if hardware has a slower growth, you would definitely see a slower growth on the software end of the things. Because working on the software, I would say a lot of, let's say, the features that I want to make would depend on do I have enough backend with me to do that. I want to work on both QPUs and GPUs, but do I have the interlinks to connect those both things? But if I don't have that, I cannot build a software on that. So it definitely is like an interdiscipline or interconnected discipline, I would say, where hardware influences the growth in the software, and maybe software also influences the growth in the hardware. So there is a lot to see and quite far away from where we currently are. Would anyone like to add anything?
Yes.
Yes.
Yeah, no, to be honest, so one thing I would say is I hope quantum advantage is not going to happen too soon, because then we will have a problem, the number of available quantum computers. Because today, there's not even 1,000 real quantum computers available. So let's say that tomorrow, one guy vibe code something with Qiskit, finds out, oh, I do have quantum advantage for one super specific case. But this super specific case, like many people will want to actually benefit from this advantage. And then, oops, there's only like few quantum computers available. And it doesn't take like 1 week to build one. It takes like months to build one. So that's why I hope that's not gonna come too early, but my guess is we're getting like very, very close, to be honest.
Thank you. Any other questions here? Yes.
So with all of this talk about quantum advantage in line, what's the hardware type that's going to push us over the finish line to do it?
Yes.
So I think you have to talk about which era. I think, in my opinion, the first one that's going to show advantage is probably neutral atom devices, just because they can have tens or like 10,000 or so in that range qubits, and their error rates are kind of getting close to where you can do error correction. So I think they'll do something scientifically interesting in the next couple of years that is definitely out of reach of classical results. But in the future, I would say you need something with maybe a higher clock rate, which, because they're necessarily pretty slow neutral atom, just for various reasons. So I would say after 5 years, I would probably bet more on a different type of device to have more advantage, but it's unclear what that would be.
Okay, could we give one more round of applause to our speakers today? Thank you very much, and I welcome you all to go into the next room for pizza, cupcakes, and last-minute mingling for the day.